Good morning, my dear NEET 2025 warriors. Welcome aboard to the Zero to Hero series targeting 650 plus marks. And this unit today of the entire optics, the ray and the wave optics, carries around 20 marks in your NEET physics. So the weightage is very good, which means in this lecture today, in this session today, you can easily boost up your score by a good amount and improve your ranks significantly to secure and grab your medical college seat in the government college. Right? So this is your Captain Shreyas on the #1 NEET English channel. Yes, make sure you're not just liking this video, but also subscribing to the channel. So thank you very much, all the warrior pandus. Hi Karthi, hi Chintu. Hello, Surva. Hello. Welcome, Chandu Atluru. Nice to see all of you back. Amruta, Tianesh, Princess. Good morning, Sugan. Yes, everybody is ready. Sudarshan. Hi, Subra. Good morning. Yep. So we are trying to do as many chapters as possible, like mentioned before also. So we are starting off with all the high weightage topics. As much as possible, we'll be doing it. And let me also remind you as we speak, there's a very important update because this thing will not be valid after 3rd of April. So right now, the NEET 2025 crash course and the DNA batch is on sale because of the festival offer. So as you can see, the link is there in the description box for the NEET crash batch in pure English for the entire syllabus 11th and 12th for 999 rupees. It's at 80% off right now, only till 3rd April. You can also get the flashcards couriered for you because last minute revision you can do using the flashcards. And many students are popularly choosing either this or this, the flashcards with the All India Test Series with the doubt solving for 4,999, 50% off. So make use of these offers for the festivities and grab this deal before it ends by 3rd of April. Yes, this is the pure crash batch for English students for the entire syllabus coverage. All right. So it's not much. I'm pretty sure you can side by side watch the crash lectures whenever required, plus the YouTube classes. So you can do a combination of both, or you can completely shift to crash. It's completely up to you. The material is going to be super. Okay, so let's begin with the class and let's start with mirrors and reflection first. Yes, thank you. Yes, Suvra, thank you so much. I'm very good, Sudarshan. Good morning. Hi, Luru. Good morning, Parima. Hi, Raghav. My headache chapter, so I'm here to become my favorite chapter. Definitely wish you all the luck. Uh, my God, such a big name. Huidrom, Indomitable Family. Wow, such a nice name. Okay, so let's begin, guys. First is the laws of reflection, which says that no matter what kind of surface you have, if it is polished, that means it is silvered, or let's say it is made reflective in nature. It's a, I can say it's a silvered surface or it's a mirror, whatever you want to say. And let's say, for example, from somewhere there is a light ray which falls onto it like this, which I call it as the incident ray, which I call it as the incident ray. Then wherever it hits the reflecting surface, I draw a perpendicular to it. That perpendicular is just called as the normal. It is called as the normal, and normal means it is exactly perpendicular to the surface. Then the reflected ray will go back like this. This is your reflected ray, reflected ray. Then this being the angle of incidence, this being the angle of reflection, the first law says the angle of incidence is equal to angle of reflection, number one. Number two, if I take a plane containing all of them, you can see all of them are in the same plane, incident ray, the normal and the reflected ray. So they are all coplanar. So that's a very important thing. They are all coplanar, means the rays are lying the same plane, nothing is coming out of it. So these are the two important things which you should know regarding reflection. And these laws are valid. They are valid for plane as well as for the curved surface, valid for both plane and the curved surface. The last important thing over here is the incident ray was trying to go in this particular direction. It was trying to go in this particular direction, but because of the reflecting surface, it has turned by some amount. It has turned by some amount. This is called delta, which is called as the angle of deviation. Angle of deviation. Angle of deviation in a reflection. In a reflection is given by delta is equal to 180 minus 2 times of angle of incidence. 180 degrees minus 2 times of angle of incidence. This is all in degrees. Please keep that in mind. So these are some important things which you should definitely keep in mind regarding the laws of reflection. Okay, Amruta, just try to refresh, see if it works. Yep, I don't think there should be any lag. Let's say, for example, it's given to you that a ray incident on a polished surface makes 40 degrees with it. Find the angle of deviation. Find the angle of deviation. That is your question, my dear students. So think about it. How are you going to solve it? Find the angle of deviation. So let's think. Maybe this was our polished surface. Maybe this is the normal. Maybe the ray which was incident was like this. It will reflect back maybe like this. As given in the question, the ray is incident on that polished surface and it makes an angle of 40 degrees with that particular surface. So sorry guys. Yeah, it makes an angle of 40 degrees with that surface. So keep in mind 40 degrees is not the angle of incidence. Yes, it is the angle made with the normal, which is the angle of incidence. So strictly speaking, this is the angle of incidence, and obviously angle of incidence will be, because this entire angle is 90 degree, so it will be nothing but 90 degree minus 40 degree, which is nothing but 50 degrees. So I got the angle of incidence, so reflection angle will also be 50 degrees, therefore, and the angle of deviation, which is 180 minus 2i, it will be 180 minus 2 times of incident angle, which is nothing but 50 degrees, correct? So 180 minus 100, 2 into 50 is 100, so this will be nothing but 80 degrees. So the deviation angle is 80 degrees. No, it is not 60. Those of you who took incident angle as 40 degrees, you would have got a completely different answer. Yep, you would have got a completely different answer. Yeah. So 80 degrees is the correct answer. Very good, Atluru, Raghav, Chintu. Very nice. Yes, I think some of you made some mistakes, but eventually, hopefully, you fell in line. Okay. Now, we will specifically discuss about spherical or curved mirrors. So, spherical mirrors, spherical mirrors. In that spherical mirrors, let's discuss all the important terminologies. First is, say for example, say for example, this is your curved surface. This side is silvered inside. So the reflecting surface is outside, then it is called as a convex mirror. Whereas if the reflecting surface is inside, it's like a cave, so that's why concave. This is a concave surface. This is a concave mirror. Now if you divide the mirrors equally into two distinct parts, then the midpoint of it is called as the pole, P or pole. Yes, this is the midpoint, which is also called as the pole of it. Then if you draw a line which divides the mirror into two parts passing through the pole, then that particular line which is there, which divides the mirror into two parts, yes, that is called as the principal, axis. It divides the mirror equally. Why is it called spherical? Because Had I continued drawing this surface, it would have turned into a sphere. So this mirror is a part of an imaginary sphere. So that imaginary sphere will have its own center as well as the radius. That is called the center of curvature and the radius of curvature respectively. So if at all I draw the radius, it will be like this. Here, if I draw the radius, it will be like this maybe. Okay. So this is then called R, which is the radius of curvature. Radius of curvature. This is also radius of curvature. This over here, this point over here is then called the center of, usually labeled C, center of curvature. Center of curvature. All right. Next important thing, if a ray or many rays are parallel to the principal axis, after reflection, you will see that they tend to reflect from the surface. If it's a convex mirror, they will diverge, and if it is a concave mirror, the rays which are parallel to the principal axis, they will converge at a particular point, something like this. So this case, it is converging. This is a parallel beam of light. Here it is obviously diverging in nature. The point where they converge, that particular point is F, which is called as the focus, of that particular mirror. Here, same way, if I extend this particularly backwards like this, somewhere here, that is where you are going to get the focus. Now, the distance of that focal point, or the focus till the pole, that is basically small f. That small f is called as the focal length of the mirror. Focal length. All the lengths, distances, everything are measured from the pole. Pole is like the origin. So everything is measured from the pole. So from the pole, F, that is focal point. From the pole, the center, that is the radius of that particular mirror. Now you should know this. If I multiply the focal length 2 times, then what I get is basically the radius of curvature. This is very, very important. You can say this f 2 times is the radius of curvature. This f and this f will become the total radius of curvature. So can I say focal point is the midpoint of center and the pole? It is the midpoint of the center of curvature and the pole. Everybody agrees with this? Yes. Hi, good morning, Pratibha. Welcome, Roshni. Hi, 0047AB. Welcome. Yes. Everybody clear till this particular point? Understood? Okay. All these are important things which you should know regarding the mirrors. Now let's come to the next part. After you understood these basic things, that whenever you want to locate the image, then remember that you can use the sign convention and the mirror formula. So let's have a quick look at the sign convention so that we can learn how to use the mirror formulas. So sign convention. What is this sign convention? You can use this for anything: mirrors, lenses, prisms, whatever you want to use, you can use it for. So you have some basically optical device over here. It could be a lens or a mirror. Okay, so it's a mirror or a lens, some kind of optical device. Okay, and let's say it has its principal axis. Always see how the incident rays are coming. Maybe the incident rays are coming like this. So I will just mark it over here. These are your incident rays coming like this. Always the pole which is there becomes your origin. Everything is measured with respect to the pole. Anything on the top is positive. Anything on the left and right will come from the sign convention. We'll talk about it, but for now, everything on the top is considered as positive. Everything above the principal axis is considered as positive, and anything which is there below below, that will be considered negative. Now, how do I decide which side is positive or negative? See the direction in which the incident rays are going. Incident rays are going towards the right side. So the right side of the pole, see the arrow mark is right side. So the right side of the pole, not where the incident rays is. See, incident rays is here. No, this side is not positive. Wherever it is pointing, right side. So the right side of the pole will be positive. So this is then the positive side of that particular system. This is the positive side. So the positive side is the side towards which incident rays point. Incident rays point. So they are pointing towards the right side. So the right side, positive is always going to be upwards. Now you don't have to ever look for the reflected or the refracted rays for the sign convention. Always focus on the incident rays. If the incident rays came from here, then obviously this side would have been positive. Now please remember, for focal length f, always measure, always see the coordinate of the focal point, or basically the focus. For the distance r, which is the radius of curvature, check the coordinate of the center of curvature. Center of curvature. For something called as u, which is object distance, always check the coordinate of the object. For v, which is always called as the image distance, check the coordinate of where the image is, placed or image is formed. This is how you need to check these distances. Although they are called focal length, radius, object distance, image distance, it's always a coordinate which you check. And coordinates are either positive or negative. Distances are always positive, mod, but coordinates are always positive or negative or zero. So although we say it is a distance, but it is technically a coordinate. Keep that in mind. I will show you some examples. After that, you will never ever face any difficulty. Don't worry about it. Okay. Similarly, the next part about sign convention is regarding the magnification. So when I say magnification, the symbol for that is nothing but small m. This magnification is the height of that image upon the height of that particular object. How many times has it magnified? If the image is 5 times more, then the magnification is 5. You can think of it like that. Now, the magnification can be positive or it can be negative. So, if this particular magnification is positive, that means the image is going to be erect. So sometimes you can see the images can be inverted. You see your upside down image. So that will be inversion. But if it is as it is, like when you stand in front of the mirror, then it is a erect image. But if the magnification is negative, then that means it is an inverted image. It is an inverted image. So let me give you some examples so that you guys get a hang of it. Say for example, my magnification is +3, then magnification is -2, then my magnification is, let's say, +1, then let's say my magnification is -0.4, then my magnification is 0.6, my magnification is -1. What do each of these numbers mean? Let's try to think about it. When it says +3, that means 100% it is erect. Not just that, because it is the number 3, it has been enlarged. So it has been magnified. So it is definitely enlarged in nature. When I say negative, the number, forget it. Negative sign means it is definitely inverted. It is inverted. And this number 2 says that I have elongated it. That means it has been enlarged. Check this number +1. Positive means it is definitely erect. 1 means whatever is the object size, same is the image size. So therefore, I can say it is the same size. The moment you see -1, then negative means it is definitely inverted. It has got inverted. If it was like this, it has got opposite. But the magnitude wise it is 1, so it has not got magnified at all. So it is same size as the object. It's just that same size just got upside down. If I say it is minus 0.4, it is again inverted, but since the number is less than 1, 0.4, so the image is smaller, so I can say it is diminished. It is nothing but diminished. Here it is 0 0.6 positive, so it will be definitely erect, and 0 0.6 is less than 1, therefore it will be nothing but diminished. Is this clear how the sign conventions work for magnification, guys? Everybody with me? Yep. Everyone? Okay, great. Awesome. So that's around 10-15th April. I mean the mid of April. That's what we are planning. Because there is one more thing which we are going to do for all of you, which is for the PYQ. And it's going to take us a long time for us to record it. So we are recording all those things. And that is also going to come. That is one of the most bumper series. Nobody has done it on YouTube, let alone any English channel. I think Hindi channels also won't do it. Okay. So we're taking some time. We are doing it for you. Okay. So let's see finally what are the formulas for our concave convex mirrors. So the mirror formulas. The mirror formulas. What are those mirror formulas? Observe it carefully. So if I have any kind of mirror, it really doesn't matter. First of all, whether it is concave or convex. Okay. Maybe there is some object over here. Maybe the rays from the object reflect somewhere. Maybe they will form some image somewhere. I don't know. Chuma, I'm drawing something. Maybe the image is formed over here. Okay, the image is formed over here after reflection. Remember, you need bare minimum 2 rays to find the spot where the reflection happens and the image is formed. Without 2 rays, you cannot ever figure out where the image is formed. So the first formula is the 1 by V plus 1 by U. 1 by image distance plus 1 by object distance is 1 by focal length. Before this, I have already told you about this. Radius of curvature is double the focal length. So that's something which I have already told. This is the first formula. Next formula is the magnification, which is height wise, which is also called as the lateral magnification or just magnification, which is height of the image upon height of the object is negative V by U. The last one is this kind of magnification, which is longitudinal magnification. Now, what is this longitudinal magnification? This means, say for example, our object was like this, the image was like this. Okay, so this had some object height, this had some image height. There will be some length of the object like this. There will be some length of the image, and all these lengths are along the principal axis. So this size will also change, not just the height, but even the width, the length might also change along the principal axis. So the longitudinal magnification, long means along the principal axis, length of the image by length of the object is the same thing, but just put V square by U square. That is the formula, guys. Length of image by length of object is negative V square divided by U square. Okay. Now, there is one last sign convention before I tell you the next formula. Magnification we did, right? So that is basically power, and power is nothing but the degree of convergence or divergence or divergence. So for example, if you have rays which are going parallelly, but maybe after reflection or refraction, whatever happens, okay, they converge. This is maybe refraction, but maybe the rays are like this. After reflection, maybe they meet over here. Okay, so this type of power is called as positive power, positive value of power. Whereas, check this out, the rays were going like this, but after refraction or reflection, they started to diverge, or the rays were going like this. Maybe they reflected and they went like this. This is diverging. So this is then called negative power. Negative power because they are diverging. They are diverging. Here, positive power because they are converging in nature. And this power for a mirror, the power of a mirror formula is negative 1 by f. Negative 1 by f, very, very important, guys, not plus 1 by f, that is for lens. And if you measure the focal length in meters, not in centimeters, because that is SI unit, the power will be measured in diopters. The power will be measured in diopters. Just let me give you an example of this. Say there is a convex mirror of radius 20 or let's say 40 centimeters. Find focal length and power. Find the focal length and the power. Come on, guys. Hi, Ramesh. Hi, Flying Itachi. Welcome aboard, everyone. I'm really glad Shreyas Sir and his team are here to support us. Obviously, serotonin. I'm not sure what serotonin does, but I'm guessing it's some biological hormone which does something very useful. I'm not that well versed with biology, but I'm so glad, guys. You guys are showing that massive support and growing this channel. And obviously, we are there till the end, and for the future students, and even for the dropper students, every single time. And this year, we are going to do something really special for your juniors again, because this year we had to build the repository. So any video, any type of thing, content you wanted to search will be there on YouTube on our Vedantu NEET English channel. Next year, we are going to take it up even at the next level. Thanks so much for all of your love. Thank you so much, guys. So how do we do this? Well, it's a convex mirror. It's clearly mentioned in the question. So it's a convex mirror. That means the rays will come like this. So they are going towards this side. So this side will be positive. This side will be negative. Is that right? So where is the focal point going to be and where the radius will be, where the center will be? This is how all the points will be. This will be the pole, etc. So can you see F is on the positive side, center is also on the positive side, and that's exactly what I told you over here. Radius and focal length can be measured by the coordinate of the focus and coordinate of the center of the curvature. So coming back over here, the radius of curvature is plus 40 centimeter. It is not negative 40 because it is on the positive side. Now focal length is basically r by 2. So it is plus 40 by 2, which is basically 20 centimeters. So focal length also 20 centimeters, which is 0.2 meters, which I will need it for power. Now power is negative 1 by f, which is negative 1 by 0.2, which is nothing but negative 5. That is, remember power units, it is in diopters. So minus 5, nothing but diopters. That is the answer. It's short form for diopters is D. Is that okay? If it was a concave mirror, then all these points will be on this side. So it will be negative. So radius, focal length will be negative. Power would have been positive. It's a convex mirror. Obviously, power should be negative. For a concave mirror, the power will be positive. Yeah. So convex, negative power. Very good. Awesome. Siddharth, it will go until 1 o'clock. All right. Now that this is done, mirror formulas and these formulas. So this is done. This is also done. This is also done. Power also, I think I blocked it. Power of the mirror. All these things are very, very important. So I think it's a good time that we start with some questions coming up on your screen. Here it is. Identify the correct statement about concave mirror. Come on, guys. Thank you, Prabodh, for reminding me to have water. Okay. Identify the correct statement about the concave mirror. What do you think? Focus both lie where? We all know if this is a concave mirror, the focal point will be here, center of curvature will be here, This will be the focal length. This will be the radius of curvature. Yes, both lie in front. Front means this. This is basically your front. This is behind the mirror. So I think C option, very good. C for Captain Shreyas, very good. Oh, that also reminds me about your types of images, real and virtual, etc. So see guys, when I say types of types of images and object. So if I see any single time that the rays of light actually meet, the rays of light, the rays are actually meeting, they are actually meeting, then such kind of an image or object, whatever it is always called as a real image or real object. And real images can always be obtained on a screen. Obtained on a screen. Example, your movie theater, your movie projection which happens, or slideshow in your school, college, sometimes you would have seen a slideshow. There is a projector which projects on the wall or on white screen. So a real image can be obtained on the screen. The rays actually meet. Wherever they meet, if you put a screen, you can see that image properly. But for some reason, the rays are not actually meeting. They are probably reflecting even before they meet, or maybe they appear to come from a point. So you have to extend them so that you see where they come from. Then, if you have to extend the rays to meet, then that kind of image which is formed is always going to be virtual. If it's an object, it will be a virtual object. Yeah, virtual object, you cannot see it on the screen. Okay, you can see it directly. You can see it directly. Example, your image in the mirror, your image in the dressing mirror. Yes, your image in the dressing mirror, maybe in the toilet or in your bedroom. If you have a mirror, whatever image you see, it's a virtual. Yeah, you can see it directly. The rays appear to come from behind the mirror, so you feel that, that's where the image is. The last thing over here is if the rays are parallel. What happens if the rays are parallel after reflection? If they are parallel, then they don't intersect. They don't intersect. If they don't intersect, then this is very important. Then there is no image which is formed. Then there is no image which will be formed. Okay, clear guys? So let's go ahead to the next question on your screen. For a point object, which of the following always produces virtual image? For a point object, which of them always produces a virtual image? Come on, guys. Thank you, Suvra, for motivating everyone. Yes, please smash that like button. Let's make it 100 likes, guys, before, continuing more. Thank you so much. Sir, this is Prakrutik. Sir, this is my brother's ID. Good morning. Hi, Prakrutik. Nice to see you. And I'm guessing your brother is quite elder to you. That's why you are using his account. So when we see the channel analytics, we see the average age of the kids or people watching us sometimes is 35 and 40. And then we used to wonder why 35 and 40-year-old people are watching our classes. Are we that good? And why are kids watching it less? Then we got to know that, okay, it's actually the parents. So maybe the parents are between the age of 35, 40, 45, whatever. So maybe that's the reason why the average age is also there in that range. And yes, we have a lot of students between 15 and 20 watching our classes. Yep, it is always which one? B for biology, B for Basilosaurus. Amazing, amazing. It is convex. Plano-convex lenses, no. Concave mirror, no. Which of them produces virtual image in air? Virtual image means something like this. So if this is a convex mirror, and if you place an object over here, if this is your object, then when you draw the ray diagram, okay, one of the ray will probably go like this, some ray will go like this. Okay, so if you extend it like this, then you will see probably an image over here. This image has to be formed by extension. So definitely it is virtual in nature, and usually convex mirrors produce diminished image and all of that. Okay. Next, focal length of a plane mirror. This is very interesting, guys. Very twisted questions. So what is the focal length of a plane mirror? This is not even a curved mirror. Come on, guys. What do you think the answer is? Plane mirror. If you take a plane mirror and you make the rays fall like that, after reflection, they will go back like this. And where will they meet? At infinity. So focal length will be infinity because the focus will be infinity. It's a polite way of saying that they will never meet. When I say they will meet at infinity, if Pandu asks Champa, when will we meet? Champa says, yes, let's meet at infinity. So the foolish Pandu thinks, okay, I will meet Champa at infinity. He gets very excited, very hopeful. He's dancing, he's singing songs, he's playing the guitar. And then he checks his watch. When will the time be infinity? When will the time be infinity? When will the time be infinity? Then slowly he realizes, oh my God, Champa fooled me. It will never be infinity. That means never. Yeah, got it? So at infinity, that is option A. Awesome, awesome. Very good. Great. Let's go. Let's go. Coming to the next question. If a convex mirror of focal length 10 centimeter is immersed in water, what do you think will happen to the focal length? This is very, very interesting question. Come on, guys. Hi, Prakrutik. I said hello. I think you didn't listen. Okay, Papa Pandu. Okay. April Fool. Oh, April Fool was. Oh, April Fool is today only. Happy April Fool's Day should never be wished. It's like you mean to say you are a fool. That's why you're wishing that person, hey, happy April Fool's Day. What are you going to celebrate happy April Fool's Day? Are you going to like dance like fools? So don't wish happy April Fool's Day to anyone unless you consider them as fools. So only two fools can wish each other happy April Fool's Day, and they'll be like happy April Fool's Day, and that person is like happy April Fool's Day. Yay. So there are two fools. Okay. It's not something that you wish. You make a fool out of a person. Okay, cool. So let's go, guys. If a concave mirror of focal length 10 centimeter, nothing will happen, guys. How will medium affect it? It will be same. It will be same. Yes, correct. So the medium has no effect on it. If the rays were coming as it is, they will go because focal length is r by 2. R is radius, 2 is a number. There is no mu in it. There is no medium in the formula. For lens, it will get affected. For mirrors, it will never get affected. Okay, very good. Let's move to the next question. All right. Come on, guys. Great. What is it? An object is placed at a distance of 20 centimeters from the pole of a concave mirror of focal length 10 centimeters. The distance of the image formed is. The distance of the image formed is. Okay. Let's draw the diagram. Object is placed at a distance of 20 from the pole of a concave mirror. So concave. Okay. So concave mirror. So let me draw the principal axis. Okay. And where is the object placed? The object is at a distance of 20 centimeter. So this is my object, and this is at a distance of 20 centimeters from the mirror. Okay. So the rays from the object, obviously, the rays from the object will come like this. So they are going this side. That means this side is positive. This side obviously is negative. For the mirror, the focal point will be here. The center of curvature will also be here. Is that right? So now let's start thinking whatever we know and whatever we need. We know the focal length, we know the object distance, we need to know where the image is formed. So use the mirror formula. 1 by V plus 1 by U is equal to 1 by F. Okay. Image distance, I do not know. Object is at 20 centimeter, but be careful. For object, check the coordinate. Coordinate is negative. So it will be at a negative 20 centimeters from the pole. Negative because it is on this side. What about the focal length? The focal length, check the focal point. It is on the negative side. So the coordinate of the focal point is negative and it is 10. So units. So negative 10 centimeters. Is that right? So therefore 1 by V. Take this on the other side. So it will become 1 by 20 and this negative 1 by 10 will be there as it is. So this will become LCM wise 20. So this will be 1 minus 2. So that will be nothing but minus 1. by 20, that is 1 by V. Therefore, V will be nothing but negative 20 centimeters. So negative 20 centimeters is option C, of course. So where is the image formed? The image is formed where the object is. Oh my God. So will the image coincide on the object? The answer is yes, kind of. But it will be, I think, inverted. And we can see that how? If you check the magnification, which is minus V by U, V is nothing but minus 20, U is nothing but minus 20. So it is minus 1. What does this minus 1 says? It says it is inverted and it is of the same size. It is inverted and it is of the same size. So the image will most likely be formed here like this. This is how our image will be. Correct? If you ask me what kind of image is it real or virtual? What will your answer be, guys? What will your answer be? Think about it. So the rays from the object reflect and meet over here. They are not behind the mirror, they are in the front of the mirror. So definitely it is a real image which is inverted and which is of the same size. In case that was asked, but it was not asked, just giving you for extra information. Is that right? Everyone, shall we go ahead to the next question? Let's go, guys. A linear object of certain height is kept in front of a concave mirror of some radius. The distance of 10 centimeter, the image formed is. Okay, just like the previous question only. So again, just try to imagine concave mirror. Let's say this blue line is only the principal axis and our object is at a distance of 10 centimeter. So this is our object which is placed at 10 centimeters. The focal point will be here, center of curvature will be here. So let's use the mirror formula to find where the image is. So 1 by V plus 1 by U is 1 by F. Therefore 1 by V plus, since the rays from the object will come like this, so this side means this side will be positive, this part will be negative. Object is placed on the negative side, so negative 10 centimeters will be the object distance. The focal length is not given, but the radius is given. So we'll do one thing. The radius of curvature is given to be minus 15. Why minus? Because it is on this side. So focal length is r by 2. So it will be minus 15 by 2 centimeters. Is that right? So put the focal length as negative 15 by 2. So take this on the other side. Therefore, 1 by V will be 1 by 10 minus 2 by 15. The LCM of this will be 30. So this will become 3 times. This will become 2 times. So 2 2s are 4. So this will become minus 1 by 30. That is 1 by V. So therefore, V will be minus 30 centimeters. This negative 30 means it is on this side. So the image is on the negative side. So this side is the real side. Is that right? So this side will be the real side. Behind the mirror will be virtual. Behind the mirror will be virtual. So 100% the image is going to be real. So real, okay, that is not asked also. We have to find the magnification then. So from the image distance, we get to know whether it is real or virtual. We do not get to know whether it is inverted or magnified from this. For that, we need minus V by U formula. So image distance minus 30, object distance minus 10. So this will be nothing but minus 30 is the magnification. This negative sign says it is definitely inverted. This, sorry, not minus 30, it is minus 3. This number 3 says that it has been enlarged. It has been enlarged. Yes. So definitely it has been magnified and it has been inverted, which is option B. B option, B for biology. Very good, Pratibha Chintu. Raghav Delvi. Awesome, Asluru. Great, great, guys. Perfect, perfecto. Awesome. Let's go to the next question. There is a convex mirror of some radius of 30 centimeter forms an image that is half the size of the object. Where is the object placed? Okay. So let's start with drawing the mirror. Let's say this is our convex mirror. Okay. So the focal point will be here. The center will be here. Forms an image that is half the size of the object. So let's say the object is over here. Let's say this distance is x, which is not given to me. The image will be formed somewhere here. I do not know where the image is. Chumma, I'll just put it over here. Chumma, it will be somewhere over here. Okay. Now we just do not know where that image is. Now the question says the radius of curvature is 30 centimeter. Since the rays from the object will go like this. So this side will be positive, this side obviously will be negative side. So the radius of curvature is given to be plus 30 centimeters. Focal length is radius by 2, so it will be 30 by 2. So therefore focal length will be plus 15 centimeters. Is that right? The focal length will be plus 15 centimeters. But that's not the end story. We have to find where the object is based on the focal length and the magnification. The image that is formed is half the size of the object. Now, we know convex mirror forms what kind of image? Virtual, virtual, diminished and erect image. Therefore, the magnification must be positive and less than 1. And since it is mentioned the image is half the size, therefore the magnification is plus half. How many of you got it? Why is it plus half? Why is it not minus half? Plus half because it will be erect only. It will not be inverted. That is the property of convex mirrors. Always convex mirrors. You have studied this in 10th standard. If you have forgotten, go back to 10th standard books. Ray diagrams and all you have drawn. It is always going to be positive, so it is plus half. Now, can magnification be written down in terms of object distance, focal length? I think so. So there is a way I can do it. So what I will do, 1 by V plus 1 by U is equal to 1 by F. Therefore, 1 by V is equal to 1 by F minus 1 by U. Therefore, 1 by V is equal to U minus F by FU. Great. So from this, I can do one thing. Take V on the top, keep U below. Take F on the top, take U minus F below. So F is on the top, U minus F below, and this will be V on the top, U here. Multiply it with negative sign, so it will become F by F minus U is minus V by U. But what is minus V by U, guys? What is minus V by U? It is nothing but magnification. Oh, that is given. We have to find object distance, and focal length is 15. So focal length as seen, it is nothing but 15, right? So that is there, minus U. Object distance we need to figure out is equal to magnification. Magnification we just saw, it is nothing but half. It is nothing but half. Okay, just have to solve this now. Just have to solve this now, guys. So 15 twos are 30, and this will be 15 minus U. So therefore U comes over here, it will become 15 minus 30. So it will become nothing but minus 15 centimeters. So object distance is minus 15 centimeters, means this x that is there, distance wise is 15 centimeters. Minus because it is on this side. So yes, minus 15 centimeters is the object distance. Is that clear, guys? Yep. Very good. Perfecto. Awesome, guys. Awesome. So these were amazing questions, guys. Amazing questions. Okay, now let's go to plane surface refraction. Reflection is done. Mirrors, curved mirrors formulas are done. Let's go to plane surface refraction. Now we all know that whenever medium changes, the light will bend. So light bends and changes speed when medium changes. When medium changes, this phenomena is obviously called refraction. This is called as refraction. So in general, let's say there is an interface and this is a normal. This is just nothing but an interface. This is a normal. Okay, this is nothing but a normal. And let's say this is medium 1, maybe air, glass, anything. This is medium number 2. And we have a ray of light which is coming like this. And then it bends maybe like this. So This is then our incident ray. This is your refracted. This is your refracted ray. This is your refracted ray. Always angles are measured with the normal, just like in reflection. So this angle will be angle of incidence. This angle will be angle of incidence. This angle will be angle of refraction. The ray was supposed to go like this, but you made it go here. So it has deviated by some amount. So the angle of deviation in refraction, not reflection, in refraction, that delta, this big angle will be I, the small angle will be R. So it will be basically I minus R, but sometimes the I is less, R is more. So we will put a mod symbol to make it always positive. Why sometimes I can be small? Because maybe it is going from rare medium to dense medium, so R can be more, I can be less. So that is the reason why we will put modulus to make it always positive. Forget the modulus, just make it positive. Even if you get negative answer, write the positive answer. So that's the meaning of it. So I minus R, because this entire angle is I on the opposite side. This is R. So from I, if you take away R, the remaining angle will be delta. So that is the angle of deviation in refraction. Okay, this is very, very important. Now, there is a specific property of a medium which is called as the refractive index. So mu, which is also called as the refractive index of the medium. Refractive index of the medium. So Snell's law says that. So Snell's law says that the refractive index of the first medium, okay, into sine of the angle in that medium, which is I, is going to be equal to refractive index of the next medium, which is over here, medium 2, multiplied by the sine of the angle made by the ray in that medium, which is basically sine R. And if there were more mediums and the light ray is getting refracted, this can be further extended to mu3 sine whatever angle, mu4 sine whatever angle it is making in that medium with respect to the normal. So this is basically your standard form of Snell's law, but obviously you can rephrase it. Yep, definitely you can rephrase it, and I'll show you how you can do that. So on the next slide. Okay, so the manner in which you can rephrase it is like this: sine of I by sine of R is equal to, think what will happen, sine R will come below, sine I is as it is, mu1 will go below, mu2 will be on the top. This is then called relative refractive index, but while writing it, we'll write it as light is going from 1 to 2, so the denominator will come here, then it will come over here. This is called as the relative refractive index of 2 with respect to 1. Refractive index of 2 with respect to 1. But while writing it, we'll write it as 1 mu 2. Not just that, if you consider how the light will be moving, see guys, over here the speed of light will be different. Here the speed of light will be different. The wavelength will be different also, but the frequency will remain the same. Yep. And we all know that the wave speed is nothing but the frequency multiplied by the wavelength. This particular frequency is something which is going to be constant. It will never change. Very, very important, guys. So the frequency is something which will not change. So if the wave speed changes, the wavelength will also change. So you will notice this ratio also becomes speed of light in the first medium upon speed of light in the second medium. Notice this is 2, this is 1, this is 1, this is 2, which is also wavelength of light in the first medium upon wavelength of light in the second medium. So this is the more generic law, I will say. Also, since 1 mu2 is mu2 by mu1, 2 mu1 will be mu1 by mu2, which I can also further write it as 1 divided by mu, but this is 2 1. So this is like the most elaborate way of writing it. All the formulas come in one single equation. Rather than remembering this, I think this is a much more elaborate, comprehensive, like a godfather formula. Everything is there in this. Is that right? Okay, very good. Awesomeness. Perfecto. Now, if by chance, the light which is entering bends towards the normal versus the light which is entering bends away from the normal, then we use these words. We say, because it is bending towards the normal, this is said to be slightly denser, but optically. This is optically denser medium. This is then said to be optically rarer medium. Here, this is said to be optically denser medium. Optically denser medium. Here it is going away, so it is optically rare. Optically rarer medium. So in this case, what happens when it goes from rare to dense medium? The angle of refraction is less than angle of incidence. The speed of light will definitely reduce because it is entering a denser medium. Also, the wavelength reduces. Frequency will never ever change. Whereas over here, when it goes from glass to air kind of medium, then the refracted angle is more than incident angle. The speed will definitely increase. The speed increases nevertheless, and also the wavelength increases. The wavelength also will increase. So this is something which you should definitely know. A very special thing happens when you're going from dense to rare medium, when you're going from the dense to the rare medium. So let's just draw a normal over here, and let's call this particular medium optically dense, and this medium is basically rare medium. So say for example, you are making the ray fall at some normal angle like this. Because it is going to the rarer medium, it will bend away from the normal. That is what will happen. So the ray which was going like this will end up going like this. If you slightly increase the angle of incidence, maybe it will go like this, and it will come out maybe like this. It will bend even more farther away like that. This creates a limitation when you're going from dense to rare. As you increase the angle of incidence, we reach a critical point. Where when that angle is so large that the refracted ray almost is like grazing through that medium's interface, something like this. This is grazing that interface. The angle of refraction is basically 90 degrees. This particular angle is then called as critical angle. I will call it IC, because after this, what happens is, if you make that light fall over here, it can't get refracted. It will only get reflected. So you will notice after this particular angle, it will get only reflected. So this phenomena is called total internal reflection. So if my angle of incidence is more than or equal to the critical angle, then I will say that's a phenomena of total internal reflection. But if my angle is less than the critical incidence, then I will say there is refraction which is happening, and partial reflection which will be happening. It is not total, so it is partial reflection will still be happening, although I might not see it so much. So there is some small bit of reflection which was still happening. It is not that much, but it is still there. It is there. So these were the rays which were getting reflected, or maybe even this was refracted. But after this angle, only reflection happens, nothing comes out. Is that okay? So that particular critical angle has a formula given by sine of that critical angle is 1 by, very important guys, refractive index of the dense medium with respect to the rare medium, which is also nothing but refractive index 1 mu 2 is mu 2 by mu 1. So mu 2 is nothing but your mu d over here. Mu 1 is nothing but mu r. So rare by dense. Obviously, rare should be on the top because sign values are always less than 1. So numerator should always be less than denominator. So you can also remember it like that. Okay, so this is again a very important formula, guys. Is that okay? Shall we proceed ahead? Total internal reflection concept, critical angle. Is there any online batch for KCT Dropper 2025? Tilak, there is no specific batch for KCT, but you can use the JEE or the NEET crash course batches for theory content, and there is a specific test series for KCT that you can use. So that link is there in the Karnataka channel. If you go to the Karnataka channel, I had made a video on that just few days back. You can just check it out. Okay. So I think it is there here. Yeah, just go with this. Just go with this particular class. You will see the link which is there in the description box. Okay, you can use JEE Crash or NEET Crash. If you want engineering content, obviously go with the JEE Crash material. KCT test series is there right over here for 499 rupees. Okay, right. So moving ahead with some questions. If a ray is refracted at an angle of 37 degrees in water from air, then find the angle through which the ray was deviated. Find the angle by which the ray was deviated. So let's have a look at it. Okay, ray is refracted at an angle of 37 degrees in water from air, then find the angle through which the ray was deviated. So the angle of incidence clearly is 37 degrees. The refractive index, it has come from air to water. So from air to water, that refractive index is 4 by 3. We all know using Snell's law, right? If you want, forget this at all. Sine of angle of incidence into refractive index of air will be sine of angle of refraction into refractive index of water. Sine of incident angle, which is sine 37, refractive index of air is 1. Sine of refracted angle, I do not know. Refractive index of water is 4 by 3. Sine 37 is 3 by 4. So into 1 will be same thing. So this is sine of r, and this is again 4 by 3. Is that right? Perfect. So what do you think will sine r be? What do you think will sine of r be? Come on guys, sine of r. Oh, was it? Oh, sorry, this was not 3 by 4. My bad. This was 3 by 5. So sorry guys. 3 threes are 9. 4 fives are basically 20. Yes, 4 fives are 20. Yep. And 3 threes are 9. So sine r is basically 9 by 20. Yep. Is that right, everyone? So 9 by 20, is it not close enough to 0.5? Very close to 0.5, approximately. Approximately. So what will r be? Whose sine is half? Almost 30 degrees. Almost 30 degrees. Is that right? Perfect. So the question now is find the deviation angle, which is angle of incidence minus angle of refraction. What is the angle of incidence? That was 37 degrees. Angle of refraction, almost 30 degrees. So approximately I can say it is 7 degrees. So it has deviated by how much? Almost, yes, 7 degrees. That is the answer. Cool, guys. Understood how to solve the question? Beautiful question. Moving ahead to the next one. Although this was a JEE question, but I feel we can still do it. Don't think, sir, JEE question, sir, how are you doing it here? Okay, it's very laddu question. Light enters from air into a medium at an angle of 45 degrees with the interference of air medium interface. After refraction, the light is deviated through 15 degrees from the direction the refractive index of the medium is. Better to draw the diagram so that we get a clear-cut picture of it. Okay, this is the interface, this is the normal. Let's think about the incident rays. It goes from air to a medium at an angle of 45 degrees with the interface of the air medium interface. Okay, after refraction, sorry. So it is coming at 45 degrees. The ray is deviated through 15 degrees from original direction. So it is going like this. Okay, so imagine this to be 45 degrees and I do not know R, but I know one thing, whatever its original direction was, from that original direction, it has deviated, the delta is given to be 15 degrees. Can you find R, guys? It is very obvious now. We all know delta is I minus R, delta is 15, I is 45. So what do you think R will be? 45 minus 15. So refracted angle will be 30 degrees. Is that right? Question is find the refractive index of the medium. So use Snell's law. So sine of incident angle, refractive index of air, sine of refracted angle, refractive index of medium. Sine of 45, air has one refractive index. Sine of 30 degrees, refractive index of the medium. Sine 45, 1 by root 2. Sine 30, 1 by 2, refractive index of the medium. So refractive index of the medium will be 2 goes on the top by root 2, which is basically root 2. So refractive index will be 1.4 approximately, but more precise, it is 1.414. Yes, B option. Very laddu question, guys. Isn't it? So sometimes, JEE mains questions are actually NEET level questions, specifically the COVID era question. Is that right, everyone? Very nice. Very nice. Great. Awesome. Awesome. Root 2. Perfect, guys. Perfect. Very good. Keep on answering the questions. Yep. Let's go to the next question on your screen. The wavelength of light in vacuum is 6000 and in the medium is 4000. The refractive index of the medium is. What is the refractive index of the medium? Wavelength is given. We just saw that there is a formula. When light goes from, let's say, air to that medium, it is refractive index of medium by refractive index of air, which is speed of light in air upon speed of light in that medium, which is also wavelength of light in air, which is also wavelength of light in medium. One big formula I was giving you. That's it. So, is the wavelength of light in the air or vacuum given? Yes, it is 6000 Armstrong. Is medium given? Yes, 4000 Armstrong. Armstrong gone. 3 zeros gone. So 6 by 4, which is 3 by 2, which is 1.5. So 1.5 is B for biology. Very good. Looks like the person who makes these options loves biology more than physics. So always B option is correct, or sometimes loves Capto. So that's why C option is correct. Very good, guys. Perfecto. Moving on to the next question. The critical angle, that is that for total internal reflection, is 45 degrees. Speed of light is this much. Speed of light in denser medium. See, critical angle, what does it give you? It basically tells you the angle after which internal reflection will happen. From that, we can find refractive index. If I know refractive index, I can find the speed of light in that medium. Oh, so that's the idea. So first, let's find the refractive index. And is there a formula for that? Yes, sine of critical angle is 1 by the refractive index of that medium. So sine of 45 degrees, because critical angle is given to be 45 degrees, is 1 by refractive index. Sine 45 is 1 by root 2. So that is 1 by mu m. So therefore, refractive index of the medium is a root 2. Just keep it on the sides. Now let's go to speed of light formula. We know speed of light in vacuum or rarer medium upon speed of light in the medium will be refractive index of the medium with respect to that air, which is nothing but refractive index of medium by refractive index of air. So refractive index of the medium is root 2, of air it is 1. Speed of light in air is 3 into 10 to the power 8. Speed of light in the medium, I do not know. Therefore, speed of light in the medium will be root 2 comes below. So 3 by root 2 multiplied by 10 raised to 8. Is that right? So 3 by root 2 means 3 by 1.414 into 10 to the power 8. So just do the math and see approximately how much are you getting into 10 to the power 8. 1.4 close to 1.5. So 3 by 1.5 is 2. So this will be slightly more than 2. Yeah, this will be slightly more than 2. So they have asked something like, what is this? 2 point something into 10 to the power 8. So I think it will be 200 and something into 10 to the power 6. So it will be 200 and something. Just check what that number is. See if it is 212, around 212. Yes, so this will be 212. So this will be 2112. Yeah, into 10 to the power 6. So that number which you are asked is 212 into 10 to the power 6 meters per second. Very good. Proud of all of you. Moving on to the next questions for apparent shift and lateral shift. Now, these are again very important questions. Sometimes people forget to discuss this. So, it's my duty to tell you about these questions and formulas and concepts. Observe carefully. Say you take below a dense medium and on the top you take a rare medium. Let's say there is a fish here. There is a fish here and the fish is at some real depth, sometimes also called as the actual depth. This is the actual depth of H naught. And the image of the fish, when seen from the top, will be somewhere over here. This will be the image of that fish where you actually end up seeing it. You are seeing that fish somewhere over here. So this then becomes H prime H1, which is then your apparent depth. The observer is here. Maybe it's a bird. Maybe it's a bird. The reverse will be when the observer is a fish inside the denser medium, then maybe you're seeing a bird which is here at a real depth, real height of H naught. And when you see the image will be somewhere far away. That will be apparent. So this is where the image of that particular bird will be. All this happens because of refraction phenomena after you draw the ray diagrams. So when you draw the ray diagrams, it is very evident why it happens. So if you take a ray like this, so you will see it will probably bend like that. It will bend like this. And when you extend the rays behind, you will see it is coming from here. So that's why it's perceived as if the object is closer to the surface. It is at a shallower depth. The exact reverse happens for this. So the bird will give out many rays, but it will bend towards the normal because it is going from rare to dense. So you will see that if any ray comes over here, it will bend towards the normal. And when you extend that particular ray, it will feel as if it is coming from here. So that is why the image appears to be farther from the interface as the actual one. In either case, what is the formula? For the apparent depth, for the apparent height, it is over here, H naught is there. Here also actual depth or height is there. But the difference is where the refractive index will come. Because I know H1 is smaller than H naught, so I have to make it small. So I will divide it by mu. Here, H1 is more than H naught, so I have to make it large. So I will multiply it by mu. That's it. That's the only difference. So if you are seeing something in a denser medium, it will be closer. So divide. If you are in a dense looking at a rare, it will appear far away. So multiply. So that's it. That is the formula for apparent depth and apparent height. Is this okay, guys? Everybody with me? Cool. Now, imagine there is a glass slab. Imagine there is a glass slab like this, and we have an observer somewhere over here. This is our observer. Let's say the thickness of the glass slab is T, the refractive index is mu. This is a slab of the glass. This is a glass slab. Then what happens is, if you look at this point, which is on the farther end of the slab, because of the apparent depth concept, this point will appear to come over here. So this point will basically have a shift, which is also called as apparent shift, which is called as an apparent shift due to a glass slab. So this surface will appear little bit closer. How much will it be closer by? The formula is whatever the thickness is there, you take it into 1 minus 1 by mu. This is the formula. This is the formula. The total thickness into 1 minus 1 by refractive index of the slab. That is the amount by which the shift will happen. Now, because this point shifts, the entire world behind it, whatever was there here, whatever was there over here, guys, whatever was there over here, this entire thing will shift as it is. Yes, this will also shift as it is. So there is a shift produced here also. All the things behind it will shift by the same amount, and that will still be delta x. So if you are looking through a glass slab, everything behind the slab will appear closer to you by this much amount. Okay, so this is the formula for it. Everybody with me? Absolutely clear? Everybody with me? Perfecto? Awesome, awesome, awesome. Great. Now, the last thing over here is the lateral shift. So one was this apparent shift, the last one is lateral shift. Observe this. Again, we take a glass slab. This is some kind of refractive medium. There is a slab over here. Oh, before going ahead, one last thing. If there are multiple layers, then what to do? Imagine there is one liquid layer here, one liquid layer here, here. Each liquid is different, of different heights, T1, T2, T3, etc. Refractive index mu1, mu2, mu3, like that. And you are looking at it from the top. What are you looking? Maybe some object over here. This object will appear to be shifted. The image will be formed here. That amount by which it shifts will be nothing but delta x1 plus delta x2 plus delta x3, like that. So delta x1 is thickness 1 minus 1 by mu1. Next is thickness 2, 1 minus 1 by mu2. How many other layers are there? You just keep on adding all those layers, apparent shifts, you will get the net shift. So this is your net amount by which the image will be shifted. Net shift will be the sum of all the shifts. Okay, keep that in mind. Now talking about the lateral shift, meaning if a ray of light enters like this, it will get refracted, and again it will refract back such that the original incident ray will be parallel to the emergent ray. Yes, it will be this emergent ray is parallel to the incident ray, is parallel to the incident ray. Basically, the deviation is going to be 0. Makes sense? This was your incident ray because it is coming back into the same medium. So let's say the thickness of this was T and the refractive index of this guy was mu. And at these points, let us draw perpendicular. Let us mark some angles. This is your angle of incidence. This is your angle of refraction. So there is a shift which happened over here. There is a shift which happened over here. But this shift is called as then lateral shift, not apparent shift. This is called lateral shift because it just shifted parallelly without any deviation. So this is called lateral shift. So this particular lateral shift delta x is given by, yep, the thickness of the slab will come, the thickness of the slab will come into observe this, sine of incident minus refracted angle upon cos of the refracted angle. That is what the formula is. Okay, so remember this formula again. I will block it over here for you. Yes, T sine I minus R divided by cos R is basically that lateral shift which occurs. Okay, thank you, Pramod, for reminding me. Let's do some questions on these. A coin is placed at the bottom of the beaker filled with water up to height of 10 centimeters. The refractive index is this much. Find the apparent depth of the coin. Find the apparent depth of the coin. Come on, guys. What is the apparent depth of the coin? See, this is the surface of the water till 10 centimeters. So the actual depth is 10 centimeters. You can think of it. The coin is over here. Okay, so the image of the coin will be somewhere, I don't know, maybe over here. This is where the image will be. So this will be apparent depth. Okay, find the apparent depth of the coin. So apparent depth will be actual depth. Should I multiply? No, it is smaller, so I have to divide. Divided by refractive index. So 10 divided by 4 by 3. So it will be 30 by 4, which is 15 by 2, which is 7.5 centimeters. So 7.5 centimeters. Sorry, I think they have given 10. Yes, 4 by 3. Yeah, it is 4 by 3, 3 goes on the top, 30 by 4, which is 15 by 2, 7.5 centimeters. Perfect, it is 7.5 centimeters. Awesome. Very good. Cool. Shall we go ahead? Sometimes they might ask you how much the shift is. If they ask you how much the shift is, then you will say the shift over here, is nothing but 10 minus 7.5. Then it will be 2.5 centimeters. So the shift will be 2.5. The depth will be 7.5. Moving ahead to the next question on your screen. There is a vessel of certain depth filled with oil and the other half filled with another liquid. What is the apparent depth of the vessel when viewed from the top? Okay, let's think about that vessel now. This is our vessel like this, and it is filled with two liquids. So first half with one liquid, the next half with another liquid. Both are equal. So this one has a refractive index N1, this one has a refractive index N2, and you are looking at it from the top, and there is some object. You can think of this as the object. And the question is the apparent depth of the vessel when viewed from the top. So what will you do? Apparent depth you have to find, right? So here is what we can do. The apparent depth usually is actual depth divided by mu, but the net apparent depth will be the net actual by mu summation. So which means actual depth of this particular liquid, well, the total depth was d, so this will be d by 2. Only this much will again be d by 2. So first one will be d by 2 is the actual depth. Refractive index is n1. The next one will be having a refractive index, sorry, depth of d by 2, refractive index n2. Both of them should be added so that we get the net apparent depth. Each one will contribute in the apparent depth, just like we could add shifts, we can add depths also accordingly. So what will this be? D by 2 is common. We have 1 by n1 plus 1 by n2. So which is nothing but d by 2, n1 plus n2 after taking LCM, and n1, n2. That is your net apparent depth. So d by 2 and n1 plus n2 by n1, n2, which is B option. B option, guys. Yeah, you can see exactly B option. Very good. Awesome. So RBS edits, to see the recordings, just go to, let's say, my schedule or something. Just go to, you will see this, my schedule. If you're on the website, on the app also, something like that only will come. Go to past sessions. In the past sessions, you will be able to see all the replays. That is one option. But if you want VBuddy repository, go to my content. Can you see here, content library and all that? Somewhere here you will get VBuddy. somewhere here in my content, you will get VBuddy. So click on that VBuddy link. That will open up a repository of recorded classes also from other teachers, so that you can get multiple perspectives for the same topic in case you need it. Is that okay, RBS edits? Very good. Awesomeness. Let's move then to the next question on your screen. It says the lateral shift when light passes through a slab, thickness 10 in air, angle of incidence is 60, angle of refraction is 45. Oh, I think I just gave you a formula. The shift is nothing but thickness sine of I minus R by your cos R. Oh, thickness is given 10 centimeters. Incident angle 60, refracted angle 45, and this is nothing but cos of 45. Is that right? Cos of basically 45, the cos R. So this will be 10. Sine of 60 minus 45 is 15 degrees. Cos 45 is 1 by root 2. So root 2 goes on the top. So 10 root 2 sine 15 degrees. That is the answer. 10 root 2 sine 15 degrees is option A, guys. So directly formula based questions can also come on lateral shift. Is that so? Okay, RBS edits, let me check on that. If that is the case, I'll just get it corrected if the content is not shown. Okay, don't worry. Okay, I know where it will be shown. I understood. Just go to content library. In content library, you will see something. There might be a link for the previous classes. Some sheet, some PDF, some links might be there in the content library. So go to my content library. In that, you might see physics, chemistry, biology. In physics, click on physics. Something will open up that will have a link of all the previous videos. Maybe there it is there. RBS edits. Just see once. Okay. Right. Cool. So let's go to the next part, which is nothing but refraction at curved surface. Here in refraction at curved surface, the main formula that you need to keep in mind and the concept that will be there, you will have a curved surface which will be differentiating, which will be like an interface between two mediums. So maybe there is medium 1 over here, there is medium 2 over here. The center of that curved surface will be again the pole. The line which cuts that surface into two equal parts, again the principal axis. That particular curved surface will be a part of a larger sphere which will have its own center of curvature and obviously its own radius of curvature. Now, if you place some object over here, again using the same sign convention, etc., maybe after refraction, the image is formed over here. This then is your object distance. This then is basically your image distance. Let's say the refractive index of this medium 1 is mu1, of this guy is mu2. Then the formula goes as follows. First put refractive index of the second medium, then put refractive index of the first medium, put minus, put equal to, then again put mu2 and then put mu1 and then put minus. Here you put a big denominator, here you put two separate denominators. Understood? Mu2 minus mu1, mu2 minus mu1. But here small denominators, here a big denominator. On the right hand side, it is always the radius of curvature, and on the left hand side, this is image distance, this is object distance. That's it. This becomes the formula for locating where the image is due to a curved surface. Very easy peasy, lemon squeezy formula. Mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. Straightforward. Let's see how to apply it so that you will understand it. Let's say there is a small object at some distance in the air from a convex surface, refractive index 1.5, radius of the curvature is 25. What is the position of the image of the principal axis? Okay, so let's again draw our principal axis and let's see our curved surface. Okay, from the convex surface, the object is placed. So if this is the thing, this is the convex side. and the object is placed at O, 0.6 meters in air from the convex side. So this is our object. This is our object, and this is at a distance of 60 centimeters from this, and it is placed in air. Air is mu1, refractive index 1. The other side, refractive index is given. This is mu2, which is 1.5. Perfect. And the rays from the object will come like this. So that means this will be the positive side. This will be the negative side. For that curved surface, the center of curvature will be here. And the radius is also given, if I'm not wrong, 25 centimeters. Perfect. So question is, where is the image formed? First, always draw the diagram from the given information. Once the diagram, sign convention, everything that you know is shown, then only proceed with the formula. Directly, if you start applying the formula, you will 100% make a mistake in the signs. Now that I know this, let's write down the formula. Mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. What is second refractive index? It is 1.5. 1.5. Image, I do not know. First is 1. Object distance, it's on the negative side, so minus 60. So 1.5 minus 1 divided by radius, it's on the positive side, so plus 25. So this will be plus 25. 1.5 is 3 by 2, so 3 by 2 is there. Minus minus is plus, goes on the other side, becomes minus again. So 1.5 minus 1 is 0.5 divided by 25. Minus minus was plus, becomes minus, so minus 1 by 60. Okay, so this is 0.5. 0.5 is half. Half is nothing but 1 by 2. 1 by 2 into 1 by 25. 1 by 50 minus 1 by 60. So LCM will be 300. So this will go 6 times. This will go 5 times. So this will become 1 by 300 is nothing but 3 by 2V. Okay, so V will be, V goes on the top, 3 goes with 300 divided by 2, which is 3 into 150, which is nothing but 450 centimeters. Is that okay? So image distance will be 450 centimeters. Is that right? 450 centimeters? Yep, perfect. So the answer is 4.5 meters, which is also 450 centimeters. Awesome. Raghav, is there any 30-day crash for NEET? Yes, there is. As you're watching this particular video only, in this video link only, this 2025 NEET crash course in pure English with your favorite teachers is there. As you can see, these are with live classes. Some classes you might get it as recording, which you can watch it at your own pace. Okay. Then you also have discussions of previous years within the class. You also get questions plus theory concepts like proper one-shots, everyday classes with full syllabus coverage, all India level test series, handwritten notes. Also, if you want revision material, especially in small cards, you can go for this version. Right now, because of the festival offer, till 3rd April, the prices are this much, 67%, 80% off. After 3rd April, these prices will get changed back. Okay, so you can definitely make use of this crash course right now itself. The link is there in the description box. Okay, cool. Moving ahead now. So I hope this much is clear for curved surface refraction. Let us go to lenses now. Usually curved surface refraction questions are very limited, but still I have done that for you. Okay. Now, for lenses, the only difference that you will see is the sign. Whatever mirror formulas, how you used it, very similar, just the sign will change. And number two, the focal length of a lens will depend on the outside medium and the medium of the lens. So how does it work? First of all, say for example, you have a lens like this. Then if a parallel beam of light falls onto it, then you will see probably it will meet over here. So this particular point will be the focal point. This will be the focal length. Whichever whichever side interacts with the light first with the incident ray, that is your first surface. So that will have its radius. That radius will be called radius of curvature 1. The other surface, which is the last surface with which the light will interact, will have its own radius. That will be radius of curvature 2. Center 1 will be here, center 2 will be here. Did you understand who is R1, who is R2? Who is R1, who is R2? Same way I can do it for a concave lens. Same thing I can do it for a concave lens. Say for example, the light is coming like this and it is going like that. It is coming like this and it is going like that. We know the focal length will be somewhere here. Focal point will be here. So this is our focal point. This is our focal length. Light has interacted with this surface first. So this first surface will have its radius of curvature R1, center of curvature C1. This is the last surface. So this will be the radius of curvature R2, center of curvature C2. Is this absolutely clear, guys? Okay. As you can see, incident rays are going towards this side. So this side will be positive. So can I say R1 will be positive? R2 will be definitely negative. Here, light rays are going this side. So center 2 or radius 2 will be on the positive side. This side will be negative. So R1 will be negative, guys. Same way, imagine if I had a plano-convex lens. Okay. Imagine again the light rays coming like this, parallel, and then probably meeting over here somewhere. So this is your focal point, this is your focal length. Light rays going this side is positive. It's coming back to the radius. Light interacted with this surface first. So that will have a radius. What? Where will be the radius? What will be the center? This center will be first one. This radius will be infinity. Why infinity? Because it's a flat surface. Any flat surface will have infinite radius because it is a part of a largest circle in the universe, which is the biggest circle which has infinite radius. So this is the first side which interacts with light. So that is R1. The second surface is this one. That will have its own radius, of course. That will be like this. The center of curvature will be here. It is on the negative side. So this will be R2, which will again be negative. Understood how the sign convention works? Okay, understood how the sign convention works? Always, whichever side the light is going, that side will be positive. Whichever side light is going, positive. Whichever side light is going, positive. For R1 and R2, check the center 1, center 2. Who is C1, who is C2? Center of the first surface, center of the second surface. What do you mean by first surface and second surface? First surface is the surface which interacts with the light first. So as you can see, this surface, light is interacting first. So for that surface, as you can see, the center will be here. This will be the radius. So that is why R1 is positive. This is the second surface. Center will be here. It is on the negative side. Same thing for plano-convex also. Flat surface, think about it, from curved, you make it big, 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 it becomes flat. The radius will become infinitely large. So the first surface has infinite radius of curvature. The second surface, obviously, the center will be here because this is the circle. So it is on the negative side. Is that okay, guys? It is on the negative side. Clear? Mahadeva? Yeah, Sukanya, after some time, we'll have a break after lenses and maybe combination. After lenses and combination, or maybe after lenses, we'll have a break. Okay, cool. Perfect. Awesome. Now, what is that focal length given by? That 1 by focal length is given by refractive index of the lens upon refractive index of the medium minus 1 into 1 by R1, 1 by R1 minus 1 by R2. That is the formula. This, remember, is the refractive index of the lens. This is refractive index of the outside medium. What you get is the focal length. This is sometimes also called as the lens maker formula. This is also called as the lens maker formula. Lens maker formula. Okay, keep these things in mind. Very, very important. Now, if you have any lens and let's say the object is here, the image is here, principal axis, everything. Where is the image form can be found by lens formula. Just the lens formula, not lens maker. So the lens formulas are as follows. This was lens maker's formula. This is just lens formula. Just like you had mirror formula, 1 by V plus was there, here you put minus. So 1 by V minus 1 by U is 1 by F. 1 by F can be found by here. Do not use R by 2. R by 2 is only for mirrors, curved mirrors. This is for lens. Magnification, which goes on like this, which is your lateral magnification. Remember, height of the image upon height of the object. That is given by just V by U. Yes, no minus over there. Only signs will change. Remember longitudinal magnification along the principal axis, which is the length of the image upon the length of the object. That is V square divided by U square. Lastly, power was not, it was minus 1 by F for mirror. For lens, it is plus 1 by F. All these are important formulas for locating image, for locating the magnification, for longitudinal magnification, and for power. Okay, very, very important, guys. Shall we go ahead? I think it's better we solve problems so that you get a fair idea. So let's start with some questions. There is a lens. This was asked in JEE 2024, but I feel it can be easily done by you guys. Has some focal length of 20 centimeters in air. Its focal length when immersed in a liquid will be how much? Very common question which is also asked in NEET. Yes, it's a very common question which is also asked in NEET. Come on guys, let's see how do we do it. The lens was having some focal length in air. So use lens maker formula. 1 by focal length in air will be refractive index of the lens upon refractive index of air minus 1, 1 by R1 minus 1 by R2. Okay. Similarly, the same lens will have some focal length in that liquid. Okay, is refractive index of the lens. This was some liquid upon refractive index of that liquid minus 1, 1 by R1 minus 1 by R2. Now, obviously, the lens will never change. R1, R2 will never change. So, it is very obvious that we have to divide both of them, because the moment I divide both of them, this and this will get cancelled. Is that right, guys? The moment I divide them, what will happen? This and this will definitely get cancelled. So, let's see what do we get with division. So, 1 by focal length in air upon 1 by focal length in that liquid will be refractive index of the lens upon refractive index of air minus 1 upon refractive index of lens by refractive index of that liquid minus 1. Nothing else will be there. So focal length in that liquid will be going on the top. Focal length of air will be here. Here, refractive index of the lens, is it given to me? Lens has a refractive index of 1.5. Air has a refractive index of 1. Upon refractive index of the lens, again 1.5. Of the liquid is 1.6. 1.6. So minus 1. So let's see what do we get. Let's see what do we get. Focal length inside the liquid divided by, in air, it had a focal length of 20 centimeters. So this is this. 1.5 minus 1 is basically 0.5, whole thing divided by, this is 15 by 16. So 15 minus 16 divided by 16. So therefore, focal length in that liquid by 20 will be 0.5 is half. 16 goes on the top. 15 minus 16 is minus 1. So focal length in that liquid will be 20 goes on the top into 1 by 2 into minus 16. So 2 goes 0 into 10 into 16 is 160. So minus 160. So focal length in that liquid is negative 160 centimeters, which is C option, my dear students. C option. Very good, Raghav. Excellent. Some of you got it. So this is how you solve the questions where a lens is kept in a different medium. Sometimes the question can be on power. So power is 1 by F. So if power is given in air, power in liquid is asked, immediately you can find whatever is asked. Usually in such questions, this number will get cancelled. So you never have to break your head about these two things. Okay? Never have to break your head on these two things. Moving on to the next question. The radius of curvature of a plano-convex lens, refractive index is given. Find the focal length, distance of the image where object is so and so, magnification. Everything is asked. So let's try to do it. Plano-convex lens. This is your plano-convex lens. Okay, principal axis. Let's put the object. Okay, where is the object? 80 centimeters. So this is where that object is at a distance of 80 centimeters, and we know that the light rays which will come over here will bend like this. So obviously this is the positive side, this is the negative side. This is the first surface. So this being the first surface, radius 1 is nothing but infinity. What about the second surface? For the second surface, think about it carefully, guys. This will be the radius of curvature, and this will be the center of curvature. So that radius 2 will be negative, and it is given to be 20 centimeters. Why is it negative? Understood? This is negative side, this is positive side. This was the first surface. Center has come on the negative side. If the center had come here, it would be positive 20. Okay. Why is this the second surface? Because light will enter this surface first, then this surface. Always the order will matter, or else you will mess up the signs. Perfect. So let's use lens maker formula and first figure out what is the focal length. So 1 by F is equal to refractive index of the lens by the medium minus 1 into 1 by R1 minus 1 by R2. That's the lens maker formula. Lens has a refractive index of 1.5. I think it is in air, if I'm not wrong. Okay, so medium is 1. 1 by R1, which is 1 by infinity, minus 1 by minus 20. So what is 1.5 minus 1? It is basically 0.5. Okay. Then what is 1 by a very large number? It is 0. Okay. Minus minus is plus. So it will become 1 by 20. So this will become 0.5, which is half, into 1 by 20, which is 1 by 40, is 1 by F. So F will be 40 centimeters. So focal length, I think we have found. Yes, this part is done. Everybody with me? Focal length is done. Okay. Distance of the image. Let's do that using lens formula. 1 by V minus 1 by U is equal to 1 by F. So 1 by V minus 1 by object is on the negative side. So minus 80. Focal length was positive. So put plus 40. So 1 by V is equal to 1 by 40. Minus minus is plus, goes on the other side as minus. So minus 1 by 80. So LCM is 80, of course. This will become 2 times, this will be 1 time. So 1 by 80, of course. So therefore, V will be nothing but 80 centimeters. So the image is formed on the other side, positive side. So this will be a real image. Why will this be a real image? Because the rays will actually meet and converge. So this will be obviously the real side. It's opposite for mirrors. This side was virtual for mirrors. For lens, this is real. This will be virtual side. Okay. Now the last part is magnification. Magnification is just V by U. V is 80, U is minus 80, so it will be minus 1. What does this tell you? This tells you it is definitely inverted, and this 1 tells you that it is of the same size. It is of the same size. So a real inverted image of the same size is formed on the other side at a distance of 80 centimeters. At a distance of 80 centimeters. Okay, 40 centimeters, 80 on the other side. Magnification is minus 1. Everything we got it. That's how you can solve these questions, guys. As you can see, they are very similar to mirror formulas. Very similar to mirror formulas. Karthi, you will get the session notes after the session is over. As you can see in the previous sessions also, when the session is over, it will be there. So let's say, for example, I go to this particular session, the modern physics session, just go down. Okay. You will get it in the notes. My God, they didn't add it. Such an embarrassment. Okay, guys, I'll get it added. Okay. It should have been there in the notes. It should have been there in the description box or the comments. I will get it added. My bad. It should have been there. Okay. I'll get it. All right. Very good. Shall we move ahead to the next question, guys? The distance between object and its 3 times magnified virtual image as produced by a convex lens is 20 centimeters. The focal length is how much? Okay, let's draw the diagram first. This is a convex lens. Okay, this is the principal axis. Okay, magnified virtual image by a convex lens. Distance between object and its 3 times. Okay, so this is the object and its magnified virtual image. So maybe it is over here. This is the image by a convex lens is 20 centimeters. So this is 20 centimeters. Let's assume this much distance as x, and we know since the rays of the object will come like this will be the positive side, this will be the negative side. The focal length is how much? The magnification is also given to me. Let's see. Can we do something with magnification and everything? Okay, see guys, magnification is V by U. Since it is 3 times magnified and it is virtual, so it is basically plus 3. Magnification is V by U. What is image distance? I think it is x plus 20. Can you see that? X plus 20. And it is on the negative side, so minus x plus 20. What is the object distance? I think you can see it. It is just minus x over here. Perfect. So therefore, minus 3x is equal to minus x minus 20. Therefore, what will happen? Yep, take this on the other side or take 3x over here. So this will become 20 is 3x minus x. So that will be 2x is 20. Therefore, x is nothing but 10 centimeters. Once I get x, we can find the focal length because I can also find object distance and image distance now. So object distance is minus x, that means it will be minus 10 centimeters. That's the first thing. Second thing, image distance will be minus of x plus 20, which is minus of 10 plus 20, which is minus 30 centimeters. So that is image distance. So let's use the lens formula. 1 by V minus 1 by U is 1 by F. Image distance minus 30. Object distance minus 10 is equal to 1 by F. Okay, minus minus is plus, so it will be 1 by 10 minus 1 by 30 is 1 by F. LCM is 30. So 10 goes 3 times, this will go 1 time, is 1 by F. So 3 minus 1 is 2. So 2 by 30 is 1 by F. So 2 by 30 is nothing but 1 by 15 is nothing but 1 by F. Therefore, F is nothing but 15 centimeters. So the focal length should be 15 centimeters. Let's check it out. Yes, it is 15 centimeters. Got it, guys? Very good. Simple use of lens formulas. Very nice. Very nice. Great. Let's just do combination of lenses before taking a short break. Okay, let's do combination of lenses quickly. Now, in combination of lenses, here is what happens. Observe carefully. Whenever you have multiple lenses in contact, it could be concave, convex, anything. It could be even concave lenses. So whenever you have thin lenses, and that too they should be in contact with each other, then they can be converted into one single lens, which is called as your effective lens. Effective lens. Effective lens. Such that the power of that effective lens will be just the addition of each individual powers with their signs. Some could be positive, some could be negative, which also means 1 by the effective focal length is 1 by f1 plus 1 by f2, like that till the last focal length. So just take the reciprocals of the focal length and add them, or just take the powers and add them directly. That is how you do thin lenses in contact. What about the magnification? The net magnification, the effective magnification, do not add them, multiply them. It is m1 into m2 into m3, like that. So there you have to multiply, do not add. For effective magnification, you have to multiply. This is 2 times, this is 3 times, this is 5 times, this is minus 3 times, minus 2 times. With the sign you multiply. Do not ignore the sign. Now, very important thing is that if you take a lens and break it into halves like this, what exactly happens? If the object was here, the rays would be coming like this. These rays will meet here. Let's say these rays will meet here. So each part will still have each part still has the same place where the rays meet. So it has the same focal length, but intensity will reduce. But intensity reduces. Very, very important. Intensity will reduce, but focal length is the same. Intensity will reduce because the number of rays which are meeting will be less. Earlier, if the lens was complete, then all the rays would meet. But if you take only one part, half the rays will meet. So that's why the focal length will be the same, but the intensity will reduce when you cut it like this. But the moment you cut the lenses like this, then each part will have a power of p by 2, half the power, because p by 2 plus p by 2 will give you the total power, which means if the focal length originally was f, each one will have 2f as the focal length. Each one will have 2f as the focal length. This is for each part. Each part will have 2f as the focal length. Got it? So that is how things will happen when you cut the lenses either like this or like this. Let's do some questions on that. The question says that there are 5 convex lenses which are kept in contact along the principal axis. The total power is 25D. Focal length of each of the lens is how much? Okay. Since there are 5 convex lenses and the effective power is given to be 25 diopters, so each lens P1, P1, P1 like that 5 times should give me the effective power, which is 25 diopters. So 5 into P1 is 25. So therefore, how much is each power? It will be 5 diopters. But wait a minute. I know the formula for power. Power is nothing but 1 by focal length of each lens. So that is 5. So focal length will be 1 by 5 of a meter, which is 100 by 5 of a centimeter. You multiply by 100, it will become centimeter. So how much is that focal length? It is 20 centimeters, which is B option. Yes, it is B option perfectly. Awesome, guys. Very good. Very good. Great. Let's move to the next question. A convex lens has some power and it is cut into 2 halves along its principal axis. One like this, second time like this. So you are getting 3 lenses now, L1, L2, L3. So consider the incorrect option for the reported pieces. Well, if the original lens had a focal length of f, when I cut it like this and like this, we know the focal length will still be the same. We just saw it here. when you cut it like this, the focal length will still be the same. So definitely this part has the same focal length. But when you cut it like that, then each one will have double the focal length. So this will be 2f, this will be 2f. Now tell me what will be the answer, guys, because obviously power is also asked. So this will be P, this will still be P, this will be P by 2, this will be P by 2. Come on, what is the correct answer, guys? What is the correct answer? Come on. Power of lengths 2, P by 2. Power of lengths 1, P by 2 wrong. Power of lengths 3, P by 2 correct. Power of lengths 1, P. P by 2 is wrong. Power of lengths 1 is P by 2. That is B option, guys. B option is incorrect. Yes, B option is incorrect. Power of lengths 2 is definitely P by 2. Power of lengths 1 is also P by 2. So, sorry, lengths 1 is P. Lengths 1 is P. Length 3 is P by 2. So, B option, I think. Yes, definitely, guys. Awesome. Let's go to the next question. In the diagram, the radius of curvature of the curved surface for both the plano lenses are 10 and refractive 1.5, the location of the final image. So first thing, let's find the focal length, guys. First of all, the radius of curvature R1 here will be infinity. Second surface, the radius of curvature will be minus 10 centimeters. Here again, this is the first surface, so R1 will be minus 10 centimeters. This is the second surface, so R2 will be again infinity. So let's find the focal length for each lens, starting with first lens. 1 by f1, refractive index is 1.5. So 1.5, medium outside is air. 1 by R1, which is infinity, minus 1 by R2, which is minus 10. So 1 by f1 is equal to 1.5 minus 1 is 0.5. Okay. 1 by infinity is 0, big number. So minus minus plus, so 1 by 10. So 0.5 into 10, 1 half into 1 by 10, 1 by 20. So focal length 1 is 20 centimeters. Same thing, now do it for the other guy. Same thing, now do it for the other guy. So 1 by f2 will be refractive index again 1.5. Outside is air, minus 1. First radius minus 10. Second radius infinity. So 1.5 minus 1 is 0.5. And this is negative 1 by 10. So this will be half. So minus 1 by 20. So second focal length will be minus 20 centimeters. Okay, so we have found out both the focal lengths. Okay, now what will happen if this is a parallel beam of light? Obviously, it's a converging lens. Obviously, it's a converging lens. So the rays will obviously meet. Where will it meet? Where will it meet? At a distance of 20 centimeters. So they will try to meet over here. In fact, somewhere like this. This is where they will meet. This will be the focal point of the first lens, and this distance will be 20 centimeters. This is where the first image is formed. This is where your first image is formed, because the object was at infinity, because the rays were parallel. Is that right? Now this image will be considered as an object for the second lens. And that object now is at a distance of, this is 20, this is 10. Obviously, this is 10 centimeters in front of it. This side is obviously positive, this side is negative. Let's use lens formula now. 1 by V minus 1 by U is 1 by F, but this is second lens. So 1 by V minus, object distance is on the positive side, so use plus 10. Focal length is negative for a concave lens, so minus 20. So 1 by V, 1 by 10 goes over there, and this is minus 1 by 20. LCM is 20. This will go 2 times. This is 1. So this is 1 by 20 is 1 by V. So therefore, V will be 20 centimeters. What does this 20 centimeters tell you? It says that the image is formed much further ahead. So whatever this lens combination was there, this lens combination was there, okay, you will see the final image being formed over here. This is 20 centimeters. This is 20 centimeters. It is going to be really far, and it is going to make obviously a real image. A real image will be formed. Is that okay, guys? Everyone? Yep. So the location of the final image after all the refraction will be at a distance of 20 centimeters. Cool. Everybody, till this point? Beautiful question on combination of lenses. Okay. First of all, when we have any two surfaces inclined at an angle which refract the light, that can be called as a prism. It need not look like a triangle. It can just have two surfaces non-parallel to each other. The angle between the two surfaces which refract the light is called as the angle of the prism. Angle of the prism. So maybe our light will enter like this, maybe. It will refract maybe like this. And finally, it will probably come out like this. So this is our incident ray. This is our emergent ray. Now we can draw normals also at both the places. So one normal like this and another normal like this. This is basically called as the angle of incidence. Angle of incidence. Let me just turn off the light, guys, because I think the light has gone. Electricity is not there. So I'm just going to be little bit dark. Hold on, I'll just see if I can increase the brightness on the camera. Okay. All right. This is called as angle of emergence. Angle of emergence. That is what it is called. This internal angle here is R1. This internal angle over here is called R2. The refractive index of the prism will be mu. Okay. Some important formulas. This angle of prism is the sum of these two internal angles. That means R1 plus R2. That is one formula. Next is the refractive index of the prism using Snell's law. Using Snell's law will be sine of incident angle by the refracted angle, or from this way, if the light enters like this will be the incident angle, which will be E. So sine of E, then the refracted angle will be R2. So sine of R2. This is also valid using Snell's law. Next important thing, the light which was initially coming was going in this particular direction. So as you can see, the light has been deviated by some amount. The light has been deviated by some amount. That is basically delta. So deviation in a prism now. We have seen for a mirror, we have seen for a refraction. So deviation in a prism, delta, is nothing but you take the incident angle, add it with the emergent angle, and then subtract the angle of prism. That is the angle of deviation. So these are some of the major formulas initially which you get regarding the prism. These are pure geometrically based. Now, when you draw a graph on the y-axis and on the x-axis, this is deviation angle versus the incident angle. That particular graph comes out to be like this. For smaller angles, the deviation is more. For larger angles, again the deviation is more. For a medium angle of incidence, the deviation is little bit less. And then comes the point of minimum deviation also. So this over here, yep. So this is your delta minimum deviation, and this happens only when incident angle is equal to emergent angle. Also you will see the internal angles R1 and R2. Remember those internal angles R1 and R2, they will be also equal. Not just that, the ray inside the ray which is there inside will be parallel to the base. It will be parallel to the base of the triangle, meaning this ray will be parallel over here. So look wise, it will probably appear to be something like this. Okay, the ray inside will be parallel, and this will go like this, this will go like this. It will be all equal, and yes, this will be the minimum deviation. This will be the minimum deviation when everything is symmetric on both the sides. The formula for that minimum deviation is as follows. Mu, the refractive index, is given by, observe this carefully, sine of angle of prism plus delta minimum, the whole thing divided by 2, upon sine of angle of prism divided by 2. This is the formula which helps you find the angle of minimum deviation, or if that minimum deviation is known, you can find the refractive index. Also keep these things in mind. I is equal to E and R1 is equal to R2. All these things are only valid when the minimum deviation occurs. Now this is true when the angle of prism is quite large over here. Here that angle of prism which was there was large. But for thin prisms, for thin prisms, keep this in mind. For thin prisms, that is A is going to be very, very small. That same deviation which you get, that minimum deviation, will be also approximately equal to any other deviation, because for thin prisms what happens, this graph is not so much U, it is like this. It's almost the same. Yes, it is minimum, but for certain value, but most of the cases it is almost the same. So that minimum deviation comes out to be nothing but the angle of prism into mu minus 1. This is only valid for thin prisms. This is an approximate formula using your small angle approximation. Okay, so that is why I put that approximate symbol over here. Is that clear, my dear students? Everybody with me? Perfect. Awesome. Now, when you have a prism like this, and on that prism, let's say white light falls. Let's say white light falls onto it. White light is made up of many, many colors. You will see the violet color will deviate the most. Violet color will deviate the most, and the red color will deviate the least. The red color will deviate the least. Yellow will be on the average. Yellow will be on the average side, you can say. So it will be something like this. Yes, you will also get other colors also. All the colors of the Vibgyor, violet, indigo, blue, green, yellow, orange, red, all those things you will get. Green, definitely somewhere over here, yellow, orange, everything you will get like this. All the colors of the Vibgyor. So starting from violet to yellow to red. Yellow is also sometimes called as the mean color. Mean means average. Mean color. Sometimes it is called as the mean color. This particular phenomena where a color or light which is incident on a refracting surface gets split into its constituent elements, constituent colors. This is called as dispersion. This is called as dispersion. And why does dispersion happen? That's a simple reason. The refractive indices are different. Refractive index of violet color is different than the refractive index of yellow color, which is different than the refractive index of the red color. And because of this, you will see the deviation of violet color is the highest as compared to the yellow color, as compared to the red color. Red color has the least deviation. And since yellow is the mean color, the refractive index of yellow is also given by the average of the two refractive indices, refractive index of the violet and the refractive index of the red color. So this also helps you solve certain problems related to yellow, violet, red colors refractive index. Keep this in mind because it is average. So that's why you're literally taking the average of the two extreme colors. Lastly, keep this in mind. There is a particular angle called as the dispersion angle. Dispersion angle. Dispersion angle, sometimes called delta theta. This delta theta is how much is the spread of those colors. How much is that spread? How much are they spreading? If it spreads more, it has more dispersion. That is nothing but always how much did the violet color deviate by minus how much did the red color deviate by. After solving, you get the answer of this particular angular spread or the dispersion, as the angle of prism will come over here. Angle of prism will come over here, and you will have nothing but refractive index of violet color minus refractive index of red color. So that is another formula which can be very, very helpful. This is related to your dispersion. Okay, keep this in mind. So maybe we can start solving some questions. Find the emergent and find the delta. Find the emergent and find the delta. Let's do this, everyone. Okay. Now, it is not necessarily minimum deviation, number one. So first of all, when the light enters over here, let's understand there will be some angle over here. Let's say we call it R1. So how do I find R1? Using Snell's law. So sine of incident by sine of R1 will be refractive index. Therefore, sine 60 by sine R1 is a root 3. Therefore, sine of R1, can you see, sine 60 is root 3 by 2, and this root 3 will go below. So this will be nothing but half. Therefore, angle R1 will be 30 degrees. So this R1 is 30 degrees. Now we can do one more thing. We can draw one more line over here. Obviously, there will be another angle R2, and finally the light will come out from here, and this will be the emergent angle. How do I find R2? There is a formula again for that. Remember, R1 plus R2 was angle of prism. R1 we found out 30, R2 we do not know. A is nothing but 60 degree. So therefore, R2 is obviously 30 degrees. So we found R2 also. Now, if R2 is 30, again using Snell's law will give me the same result, guys. So sine of E by sine of R2 being refractive index. So sine of E, sine R2 means sine 30 is a refractive index which is root 3. So sine of E will be root 3 into half, root 3 by 2. So therefore, emergent angle is again 60 degree. That's it. Last is the deviation angle. Deviation is I plus E minus A. Incident angle 60, emergent angle 60, angle of prism 60. So it is 60 degrees. So deviation is 60 degree. So beautiful question on finding each and everything of that particular prism. Is this absolutely clear, my dear students? Shall we go ahead to the next question? Okay. Perfect. Let's go. Great, great. Let's go, guys. Let's go to the next question coming up on your screen. A prism is made up of flint glass such that the incident ray does not emerge from the next surface. The critical angle for the flint glass, I think 36, 37 degrees. Then the refracting angle A must be how much? Okay. So I think we will take it as 37 only. 36, 37 is almost the same. So let's draw a prism first of all. A prism made of flint glass as the incident ray does not emerge from the second surface. The critical angle for flint glass is 36 degrees. Okay. That is what is given. Then the refracting angle such that the incident does not emerge. Okay. Now, in this particular case, think about it. No matter what you do, it should not come out from the other side. It should not come out from the other side. So which means, let's say, in the worst case, it is grazing incidence. It is just coming out like this. So this is your grazing emergence. It is grazingly emergence. So therefore, if I draw perpendicular here, this particular ray will be like this maybe. And again, if I draw a ray like this, then we will have something like that over here. Now, since it is grazing emergence, so this particular angle, by the way, instead of 36, let me put it as 37, that will be better. Okay. So if this is grazing emergence, this angle R2 will be that critical angle, which is nothing but 37 degrees. That is 100% sure. Correct? This will be nothing but 37 degrees. Okay, everyone with me? A prism is made up of flint glass such that the incident ray does not emerge from the next surface. The critical angle for the glass is 37 degrees. That is already given. Then what is the angle of that prism, they have asked? What is the angle of that particular prism? But if I'm not wrong, they have not given the angle of incidence or anything else as such over here. Okay. Okay. So if this is R1, this is R1, they have not told anything about it over here. I think there is something missing, maybe. Okay, I'll see what is missing. Maybe we'll take it up some other time. Something is missing. Anyways, we will do it some other time. Okay, we'll take up the next question. Okay, prism having refractive index and reflecting angle 30 degrees has one of the refracting surface polished. Okay, a beam of light incident on the other refracting surface will retrace its path if the angle of incidence is. I think this will be prism having refractive index. This will be refracting angle, I think, not reflecting. Okay, so anyways, we'll start drawing the diagram. This particular angle and the angle of the prism is 30 degrees. So that means this is basically 30 degrees. The one of the surfaces is polished. That means, let's say this surface is polished like a mirror. It behaves like a mirror. A beam of light incident on the other surface will retrace the path. Oh, if it has to retrace the path, that means the light should fall perpendicular on that polished surface. Only then whatever is incident will retrace back. So if I draw a normal over here, then what should happen is that the light which comes like this should come back like that. That is what should happen. This is my angle of incidence. This is my internal angle. Let's say I call it R or R1, whatever you want to call it. This is how they are going. Okay, now if this is 90 degree, obviously this is also 90 degree. In this right angle triangle, easily you can see that this particular angle will be now 60 degree. So this particular angle R will be 90 minus 60, which is nothing but 30 degree. Okay, and what else is given? What else is given? Prism having refractive index is also given. So therefore, using Snell's law, sine I by sine of R being mu, sine of I, refractive angle is 30. So sine 30 is refractive index. So sine of I is root 2 multiplied by sine 30, which is half, which is 1 by root 2. So sine of I is 1 by root 2, meaning incident angle is 45 degree. Incident angle is 45 degree. Very good. Awesomeness. Awesomeness. So that is the correct answer, 45 degree. So these kind of questions are very, very common, guys, in your prisms. Okay. So let's go now to the wave theory concepts. Wave theory, many important things are there in wave theory. Light waves, wave optics, we have come to. First of all, let's talk about light wave. Light as a wave shows the following characteristics, like it can refract or even reflect. It can also interfere with each other, interference. It can also basically, diffract. Diffraction phenomena is also a wave phenomena. And the speed of light is always the frequency multiplied by the wavelength. This is standard formula. And light wave is nothing but a electromagnetic wave. We will see electromagnetic wave in a separate chapter. That is not today's concern. Today we are just seeing some wave characteristics of light wave, like reflection, refraction we have already seen. Interference and diffraction is the main concern over here. Okay. Yeah. Now when light was considered as a wave, initial theory was light was a mechanical wave governed by Huygens, but that was later on disproved. But still, Huygens was able to explain certain phenomena. That's why Huygens theory was considered or given some amount of interference. So, as per Huygens wave theory, wave sorry, Huygens wave theory. Okay, Huygens wave theory. Light is a mechanical wave, as per him. Light, light is mechanical wave. Number one. Number two, the medium which is used to travel, the medium which is used to travel is called as ether. Is called as ether. He said the source produces disturbance in the medium. The source produces disturbance in that medium which travels, disturbance in that medium which will travel in all the directions, and the locus of all the points, locus of all the points with same disturbance, with the same disturbance, basically the same phase, that is called as the wavefront. That is called as a wavefront. And the disturbance which is produced in that medium, that will travel, the traveling direction is called as the ray of light. It's called as the ray of light. So if you have a source, let's say like this, the rays of light will go like this, like this, like this, like this. So these will be the rays of light, and the perpendicular to that will be the locus of all the points with the same phase, same oscillation, same disturbance reaching at the same time. They are basically your wavefronts. They are basically your wavefronts. He also gave a way by which you could predict the wavefronts after some time. So that is also called as Huygens construction. So Huygens construction. Huygens construction says that if you have, let's say, some wavefront like this is called as your primary wavefront. And we know that the wave is traveling like this. It is traveling in this particular direction. If you want to find how will it look after some time, he said that you take any point on the primary wavefront. In fact, all the points on the primary wavefront, they will act like new sources. They will act like new sources of light, which are called as secondary sources. What will these secondary sources do? They will emit their own wavefronts, and their wavefronts will have a size of c into t. C is the speed of light, t is the time after which you want to find the wavefront. Each of them will produce new wavefronts, but in which direction? They can produce it behind also, in the direction of travel. The radius of the secondary wavefronts, the radius of the secondary wavefronts is equal to speed of light into t. T is the time after which you want to find those wavefronts. Then he says you just have to draw a common tangent to all these secondary wavefronts. The common tangent that gives you basically the new wavefront after time t. That will give you the new wavefront after time t. That is basically Huygens construction to find the new wavefront after some time. So he says every point acts like a secondary source. They will generate secondary wavefronts. The common tangent will give you the new wavefront after time t. That's it. That is basically Huygens construction. Is that okay, everyone? Next important thing, observe. There are three types of sources and their intensities, how they change with time. How they change with distance. So first is called as a point source. Next, line or cylindrical source. Line or cylindrical source. This point sometimes is called as spherical also. Spherical or point source. Last is called planar source of light. Planar source of light. So when you have a point source versus a line source versus a planar source, what is the difference? Observe. The light will travel in all the directions. In case of point source, all up, down, front, bottom, everywhere. In cylindrical source, it will go radially outwards like this in the form of a cylinder. You will see that once I draw the wavefront, it will be very, very obvious. In planar, it will go just straight in front of it like this. So here, if I had to draw the wavefront, it will look like this. This is how the wavefront will be. So that will be also planar in nature, planar wavefront. Here the wavefront will be cylindrical in nature. The wavefront will be cylindrical in nature. Cylindrical wavefront. Here, in the first case, the wavefront will be spherical in nature. So this will be spherical wavefront. Perfect. Now what happens is that if you say that the power of the source is P, then the power is back, and let's continue, guys. I'm so sorry for that brief interruption, but finally when the session will be recorded, I think you will get a continuous stream. So let's continue, and please let your friends know that Shreyas Sir is back. So we were talking about the spherical wavefronts, cylindrical wavefronts, and the planar wavefronts. At these places on those wavefronts, the intensity of light will be at every wavefront. The intensity of that light will be a very interesting term. The power of the source will come in the numerator. The power of that particular source will come in the numerator. And below, what you will get is a area of that wavefront. The area of that wavefront, like we all can see, for this spherical wavefront will be 4 pi r square. For cylindrical, the curved surface area will be 2 pi r multiplied by the height. And in this case, the area will be constant. So this is a very special case where the intensity never changes. It will always remain a constant. Here, the intensity is inversely proportional to the distance. Here, the intensity is inversely proportional to the square of the distance. That's the big change. Is that okay, my dear students? Everybody, till this point? Okay, I hope I'm visible and audible to all of you. Yeah. No, there was no network problem for you guys. Yeah. So, great. Great. Perfect. Now, also keep in mind one more thing regarding intensity and amplitude. Always this is true. The amplitude's square is directly proportional to the intensity I. Intensity is directly proportional to the square of that particular amplitude. Keep this in mind. Okay, all these are very important formulas regarding the sources and how they are changing with respect to the distances. Okay, so let's do a question. The amplitude of light from a source which is 5 meters from a position is A, then at a distance of 15 meters from the source, what will be the amplitude? That is the question. Okay, is amplitude directly related to the distance? No, but I know that the square of the amplitude is related to the intensity, and the intensity is related to the distance inversely and square proportional. So if intensity is proportional to this, intensity is inversely proportional to this, what do these two statements together tell me? Square of the amplitude is inversely proportional to the square of the distance because it is a point source. That is why I'm using 1 by r square. If it was cylindrical, 1 by r. If it was planar, it will be a constant. Keep that in mind. Okay. So both sides are squared, take square root. So A will be inversely proportional to R. Therefore, final amplitude by initial amplitude will be first distance by the last distance. New amplitude, I do not know. Old amplitude is A. The old distance was 5 meter. The new distance is 15 meter. Therefore, A2 by A is 1 by 3. Therefore, A2 will be nothing but A divided by 3. A divided by 3 is option number A. So this kind of questions you can get related to intensity and amplitude. Okay, it's completely based on this slide. Huygens principle questions are very straightforward, how the wavefronts will look like, purely theoretical. Now let's go to the main part, which is the interference part. So very important, my dear students. Let's have a look at it. Interference of waves is where two or more waves meet at a point and they produce something called as the resultant. But before they meet, there is something called as what is the difference in their path. Meaning, when the two waves arrive, maybe their crests might arrive at the same time. Maybe when the crest arrives, the trough of the other wave arrives. Depending on that, the interference can be positive, as in constructive, or negative, meaning destructive. Or maybe neither constructive nor destructive. It's somewhere in between, called as intermediate interference. So, when the waves interfere and meet at a point, what matters the most is, are they in the same phase or is there any phase difference between them? So, how to calculate that? So, say for example, the two waves meeting at a point look something like this. This is one wave. This is another wave. This has some amplitude A1. This has some amplitude A2. As you can see, between them, there is some distance or some gap, some lag or some lead is there. It's like two cars moving on the same road, but one car is behind the other. So how much is that gap is called as the path difference. That path difference. Now this path difference can be caused because of multiple reasons. Multiple reasons. We will come to it in a bit, but definitely there can be a path difference between the two interfering waves. So these are two interfering waves. These waves can also have some intensity. Let's say this has intensity I1, let's say this has intensity I2. Now, once they have some path difference, there is also something called as the difference in the phase or phase difference. Phase difference. Phase difference, which is delta phi. This delta phi is given by 2 pi radians divided by lambda multiplied by the path difference. As simple as that. Multiplied by the path difference. That's it, guys. So that is the phase difference formula. The difference in the phase between the two waves which are meeting at a point. This is always expressed in radians. This is always expressed in radians. Now, what do we exactly want? We want to find the resultant wave. So the resultant wave will have maybe some equation, maybe YR, which is the direct addition of each wave being superimposed or which is interfering. This is also called as superpositioning. Superpositioning of waves, where you add those waves to get the net resultant. But remember, these are instantaneous displacements, instantaneous values. They are not the amplitudes exactly. So each wave will have its own equation, maybe something like this: A sine maybe kx plus or minus omega t plus maybe phi 1. Other wave might have some other amplitude, same sine kx plus or minus omega t plus phi 2. Correct? This phase difference which we got over here technically was phi 1 minus phi 2. That phase difference which we got over here was this phase constants difference. When you combine both of them, you should get a resultant wave, some sine kx plus minus omega t plus some resultant phi. I am interested how much is this resultant amplitude going to be. I am interested how much will be the resultant amplitude. That is what I am interested in. So to find that, the logic is simple. Okay, there was some part difference, there was some phase difference, all these things we found out. Let's say you add both these waves. Let's say you add both these waves and you get basically the resultant wave. The resultant wave, let's say, has some new amplitude AR, new intensity IR. How to find the resultant wave's amplitude? It is done via vector addition of the phasors of the waves. So the resultant of resultants, the resultants amplitude of the two interfering waves is is found by vector addition of the phasors of the phasors. Phasors are basically those imaginary quantities which tell you in which situation that wave is right now, and the length of a phasor is always the amplitude, and the phasors are always rotating with the same omega or angular frequency as in the wave equation. So they keep rotating and they have a length equal to the amplitude, and they might be not together, they might have some phase difference, that same phase difference which I'm talking about. So what you do is, if these are the two waves which I have to add, just do one thing. Just take one of the amplitudes, show their phasor, take the other phasor, show that amplitude. Let's say this amplitude is A1, this is A2. The angle between them will be basically delta phi, that is their phase difference. Remember, you will get delta x, that will give you delta phi, right? That will give you delta phi. So that same delta phi, you put it over here, then find the resultant using vector addition. So maybe this is the resultant. You can use parallelogram law, triangle law, whichever law you want, use that law. That will give you basically the resultant's amplitude. So you will notice this AR will be root of first amplitude square, second amplitude square plus 2A1 A2 cos delta phi. Similarly, the resultant intensity the resultant intensity is given by first intensity plus second intensity plus 2 times root I1 I2 into cos delta phi. That's it. So that is the formula, my dear students, for finding the resultant's amplitude. Yes, finding the resultant's amplitude or finding the resultant's intensity. Anything. You can use this. Is that okay, everyone? So this is how you find the resultant wave's amplitude by vector addition of the phasors. Phasors are those imaginary quantities which keep rotating with the same length as the amplitude, and they might be pointing in different directions depending on their situation, meaning phase, which phase they are in. Okay, cool. Yeah. Yeah. I know, Mohan Raj, I'll be coming to that J session after this session is over. Okay. So, a lot of things got messed up because of the power cut. So, I will come there. Don't worry. Meanwhile, take a break over there. All right. Now, there are two kinds of interferences which can happen. One is basically called your constructive interference. Constructive interference. The second one is called destructive. Destructive interference. So in constructive interference, what happens is the two waves are in sync such that such that such that the resultant the resultant is even bigger. That is the resultant, and the resultant simply is the addition of the two amplitudes A1 plus A2. That's it. The crest with the crest, trough with the trough becomes a big crest, big trough. That is the resultant amplitude. And this amplitude is always the maximum amplitude possible. Even you get maximum intensity, the resultant intensity is maximum, and it is given by very important formula, root of I1 plus root of I2 the whole square. That is the maximum intensity possible. Talking about the phase differences, the phase difference and the part differences can be 0, 2 pi, 4 pi, basically any even times of pi. They are said to be then in the phase. When the phasors are in the phase, then that is the phase difference. Basically, if you see the phasor diagram of these two things, they will be one behind the other like this, and the resultant will be in like this. So this is their resultant, which will be nothing but A1 plus A2. That's why they are said to be in the same phase. If you talk about the path difference between them, it can be either 0, it can be lambda, it can be 2 lambda, in general any n times of lambda. Then you will see the waves are constructively interfering. But when they are destructively interfering, their crest will meet with the trough will meet with the crest. That's what will happen. So when you add both of them, this has amplitude A1, this has amplitude A2. So you will see one of the phasor is like this, the other phasor will probably be like this, slightly. Okay. So the resultant will be like this. So this is your resultant. This resultant will be smaller. This resultant will be smaller, and this AR, or even this will be minimum amplitude. This will also give you minimum intensity of that resultant will be just A1 minus A2, whichever is bigger. So I'll put a modulus symbol between them. So this is A1, this is A2. So A1 minus A2 will be resultant. That will be a smaller amplitude. This is destructive interference. Intensity will be root I1 minus root I2 the whole square. Just like it was plus here, it will be minus here. The phase differences possible are either pi, 3 pi, 5 pi, 7 pi, basically odd pi's are possible. They are said to be then out of phase. Out of phase. Path difference wise, it can be lambda by 2, 3 lambda by 2, 5 lambda by 2. In general, odd times lambda by 2. That is what the path difference will be to give you destructive interference. Okay. So keep all these theory points in mind. Then we can proceed ahead. Shall we, my dear students? Pakka? Okay. Very good. Let's go to some questions now coming up on your screen. All these formulas, everything on this slide is important. So I'm not blocking anything. Every single piece is important. So let's do. Amplitudes of the interfering waves are in the ratio 2:5. Then the ratio of the maximum to minimum intensity is how much? So it's mentioned the amplitudes of the waves which are interfering is given to us. And the question says maximum to minimum intensity is how much? First, what's the maximum amplitude possible? It will be A1 plus A2. So if their ratio is 2:5, assuming 2 and 5 as the amplitudes, it will be 7. And the minimum amplitude will be A1 minus A2, the mod of it. So it will be 2 minus 5, which is basically 3. But we know one thing, that the intensity is proportional to the square of the amplitude. So the maximum intensity by the minimum intensity will be maximum amplitude by the minimum amplitude, the whole square. Is that right? Minimum amplitude, the whole square, because it is square proportional. So what is the maximum amplitude? That's 7. Minimum is 3. So 7 by 3 whole square. So this will be 49 by 9. So 49 by 9 is B option. That's it. So that will be the ratio of the maximum possible intensity by the least possible intensity of the two waves. Maximum will happen if they are in sync constructively. Minimum will happen when they are destroying each other destructively out of phase. Is that okay, everyone? With me? Cool, guys. Perfect. Let's do one more question coming up on your screen. Here it is. Here it is. If the maximum to minimum intensity of two waves is 16 is to 9, then find the ratio of the intensities of the two waves. Then find the ratio of the intensities of the two waves. Let's try to do this particular question, my dear students. So as per the given question, maximum by minimum intensity ratio is given to be 16 is to 9. By formula, we know this. By formula, we know this. Where is it? Maximum intensity is this. Minimum intensity is this. Constructive, destructive, maximum, minimum. Same thing, but with a plus and minus sign. So let's go back over here. Let's go back. Maximum will be root of I1 plus root of I2. Minimum will be root of I1 minus root of I2. But this is also squared. This is also squared. So that is 16 by 9. Taking square roots on both sides. So I'll get root of I1 plus root of I2 upon root of I1 minus root of I2 is nothing but 4 by 3. So now you'll use componendo dividendo property. So componendo dividendo property. So you add numerator to the denominator. So root I1 plus root I2 plus root I1 minus root I2 upon numerator, which is root I1 plus root I2 minus denominator. So root I1 minus root I2 over here. So numerator plus denominator, numerator minus denominator is equal to 4 plus 3 upon 4 minus 3. That's what I will get after this property. What will happen? I2 will get cancelled. So it will become 2 root I1. Here, I1 and I1 will get cancelled. I2 will get added. So 2 root I2 will be 7 by 1. 2 gets cancelled. So root of I1 by I2 is 7 by 1. So therefore, I1 by I2 square it will be 49 by 1. So the ratio is 49 is to 1. So the ratio is basically 49 is to 1. Is that right? Let's go to the next question coming up on your screen. If two waves of amplitudes A and 2A having wavelength lambda have a path difference of lambda by 4, then amplitude of the resultant is? Amplitude of the resultant is how much? That's the question. Let's try to think about it. Amplitude of the resultant is asked. Obviously, path difference being given, we have to find the phase difference, without which we can't find the resultant. So first, let's focus on phase difference. The formula is 2 pi by lambda into delta x. I just gave it to you over here. Delta phi is 2 pi by lambda into delta x. Okay, fair enough. So let's go over here and write down the formula for delta x. What is the path difference? It is clearly mentioned as lambda by 4. Lambda lambda cancels, 2 cancels. It will become pi by 2. Oh my god. That means one of the wave phasor is like this. The other wave's phasor is basically like this. The resultant is like this. And they both are at 90 degrees with respect to each other. So that means the resultant using Pythagoras directly I can get it root of a square plus 2a square using Pythagoras theorem. Using Pythagoras theorem. A is common, 1 plus 2 square is 4. So the answer will be a root of 5. The answer will be a root of 5. Is that absolutely clear, my dear students? Very good. Awesomeness. That is the correct answer. Perfect. I think this slide came by mistake here. Shift it back. Okay, done. Now let's see the formulas related to Young's double slit experiment, YDSE setup, where what happens is you have a screen where in a dark room you have a screen and you have a opaque board, opaque obstruction or a wall or something in which you cut out two slits. I will call them slit number 1, slit number 2. These are your slits which are there. And the separation between these slits is basically D. The separation between the slits is basically D. And then here you have a source which is monochromatic in nature. Monochromatic means single color, not multiple colors. Monochromatic source. Monochromatic source is there. That's what you do. And this monochromatic source will emit wavefronts in all the possible directions and it will emit rays in all the possible ways. So the rays will go everywhere. Some of the rays obviously will get blocked by it. Some of the rays will get blocked by it. So the wavefronts which will emerge will be like this. This is how the wavefronts will emerge. After this, these two sources by Huygens principle will act like a secondary source. So you will see they will act like secondary sources. They will act like secondary sources emitting secondary wavefronts. This one will also act like secondary source emitting secondary wavefronts like this. And these two waves will now interfere with each other. If you go at any place on the screen, let's say for example, this point here and this point here, this particular point where they interfere on the screen. So this is the point of interference. As you can see, both the rays travel different distances. That's the reason why they will not arrive simultaneously. There will be a path difference. So if you by chance drop a perpendicular like this from here to here, the length of the perpendicular being d, which is much larger than the small d value. This is that small d, if you have forgotten. This is that small d. Distance between screen and the slits, this is the distance between the slits. Then, if they make an angle theta in general, if these two waves, they are very far away from that screen, but very close at the start, if they are making some angle theta over here, then the path difference at that point at that particular point is just given by this d which is there, into nothing but sine of theta. D into nothing but sine of theta. This is a very, very important result. Okay, for the part difference in a Young's double slit experiment. This is the part difference. And we know what happens if it is constructive versus destructive. For constructive, sorry, I put delta phi, my bad. It was delta x. Sorry, this was delta x, part difference. For constructive, you will see it should be any n times lambda. And destructive, for destructive, it should be odd times lambda by 2. How did I get that? Just give it to you right over here, guys. For constructive, any n lambda. For destructive, odd times lambda by 2. That's all. What happens exactly at constructive and destructive interference? At destructive interference, both the waves will destroy each other. That means there will be a complete dark region over there. At constructive interference, they will meet and produce bright region over there. So there will be a bright region in the place of constructive interference. So what you will see eventually is alternate on the screen. What you will see eventually is alternate bright and dark regions. You will see alternate exactly in the front. It will be bright, then again dark, then bright, then dark, then bright. So you will see something like this on the screen. This is called as a fringe pattern. What is this called? This is called as a fringe pattern. On the screen, or you will see a fringe pattern, on the screen. Now, from one bright to the next bright, or from one dark to the next dark, anything that you want to call. So from one dark to the next dark, or from, let's say, one bright to the next bright, anything, guys. Okay, even this for that matter. That is called beta, which is lambda capital D by small d, which is called as the fringe width. What is it called? It is called as the fringe width. Yep, that is called as the width of the fringe, or the fringe width. Lambda is basically the wavelength of the light which is used. Okay, this capital D and small d, those are exactly these things. This small d is this, and capital D is basically the distance from the screen to the slits. That is your capital D over here. That is your fringe width. Keep this in mind. Now, if the medium is in a if the entire setup is in a different medium, then lambda will change. So I will put a star mark over here, that if medium changes, if the medium changes, then obviously the new lambda will be the old lambda divided by the refractive index of that particular medium. So if you put it in water, refractive index will be there, lambda will decrease, so fringe width will reduce, so the entire pattern will shrink. The entire pattern will definitely shrink. Exactly in the front, what you get is the central maxima. What you get is basically the central maxima, also called as the 0th maxima, which is basically bright in region. Maxima because it is maximum intensity. Then you get minima, which is basically dark. Minima, which is basically dark. Then you get again a maxima, minima, maxima, minima. So you get a fringe pattern on the screen where the bright fringe due to constructive interference, that is called as maxima points, maxima regions, and the dark regions due to destructive interference is called as minima. It is called as minima. Is that absolutely clear? Now, if you go to any particular place and you want to know what is the location of the bright fringe or what is the location of the dark fringe, here is the formula for that. So say for example, you want to know where is the nth bright fringe? Where is the nth bright fringe? Nth bright fringe. Nth bright fringe. The formula for that, is very simple, guys. It is nothing but n times beta. That's it. N times of beta. That's it. That is the answer of the nth bright fringe. Very, very simple. Okay. So it is just nothing but n times of beta. But if you want the nth dark fringe, if you want any nth dark fringe, then what is the formula? If you want any nth dark fringe, okay, then what is the formula? The formula goes as follows. Any nth dark fringe is n minus 1 by 2 into beta. That's it. So if I want the first dark fringe, 1 minus half, so beta by 2. Yes, that's perfect. So that is for basically dark fringes. N minus half into beta for any dark fringe location. For any dark fringe. Fifth dark fringe, 5 minus half, 4.5. 4.5 times beta. Beta is your lambda d by d. Beta is your lambda d by d. That's it. Is this absolutely clear? How do you locate any of the fringes? Last thing over here, my dear students, is the angular width of a fringe. The angular width. This is also sometimes very important. This is, let's say, delta psi, which is called as the angular fringe width. Angular fringe width. That is given by whatever fringe width you get is the length of the arc. Think of it like that. That is length of the arc. This is radius, which is d. So length of the arc is radius into theta. So theta is length of the arc, which is nothing but your beta over here, divided by the radius. Think of this as an arc. This is fringe width. This is your radius. So angle is length of the arc divided by the radius. So the radius being d. That's it. So that is the formula for the angular width of any fringe. Angular width of any fringe over there. Keep that in mind. Great. Now, what happens when we start solving? Okay, let's start solving problems now. Fringe width in a particular YDSE is measured to be beta. What will be the fringe width if the wavelength of the light is doubled, the separation between the slits is halved, and the separation between the screen and the slits is tripled? So many things have happened all together. Let's try to understand. So, fringe width, what will be the fringe width if the wavelength, okay, let's see. So the new fringe width, I do not know how much will it be. The wavelength of the light is doubled, so 2 times lambda. The separation between the slits is halved. That means this d is by 2. Separation between the screen and the slits, that means capital D, is tripled. Okay, so what will it be? 2 2s are 4. 4 3s are 12. So this will become 12 times lambda d by d. But wait a minute, what is this lambda d by d? It is beta. So it will be 12 times of beta. So the new fringe width is 12 times. So which is option D, I believe. Yes, it is the correct answer. It is just going to be 12 times. Very good. Awesomeness. Next question coming up on your screen. YDSE, the separation between the sources is halved and the distance from the screen from the coherent sources is redoubled. Okay, then the fringe width will become. Well, let's see what has happened in each case. The separation between the sources, that means S1, S2, is halved. That means D has now become D by 2. The distance of the screen from the sources is doubled. That means capital D has been made 2 times. So what will happen to the fringe width? Okay. So if the old fringe width was lambda D by D, the new fringe width will be lambda is the same. D has become 2D. Small d has become D by 2. So 2 2s are 4. lambda d by d, but this is old fringe width, so it is the 4 times of the old fringe width. So answer is B, I believe. So this has come in NEET 2020. So these are the kind of questions that usually they ask. Is that okay? Great. Let's move to the next question coming up on your screen. Right. In a YDSE, a student observes 8 fringes in a certain segment of the screen when the light is of 600 nanometers. If the wavelength of the light is changed to 400 nanometers, then the number of fringes will be how much? Okay. So let's say this is that segment of the screen, and in that you are seeing some fringes. You are seeing some fringes over here. Okay. Whatever is the fringe width, like that, the first fringe, second fringe, like that, n fringes will be there. The total length of that segment, can I say, is the fringe width into the number of fringes that you see in that segment? Beta, 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 n times will be L, the length of that, that segment. But the length of the segment is the same, observed in the same region. So this is going to be the same, reason being in the same region they have asked. So in the same region. So can I not say beta 1 n1 will be beta 2 n2? Beta is lambda d by d. This is n1. This will be lambda capital D by D. This is n2. dd cancels. So lambda 1 n1 will be lambda 2 n2. Lambda 2 n2. What is the wavelength? Is it given to us? Yes, light is 600. The number of fringes that you see is 8. When the light is 400, how many fringes will you see? 0, 0, 0, 0 cancels. So you have 6 into 8 divided by 4 is n2. So n2 will be 8 by 4 is 2, 2 6 are 12. So answer will be 12 fringes, which is option A. NEET 2022 question, guys. This is NEET 2022 question. Yes, perfect. Awesomeness. Moving on to the next question on your screen. Statement based in YDSE setup, two statements are given below. If the screen is moved away from the source or the slits, the separation remains same. If the source is replaced by another light source of larger wavelength, the angular separation decreases. I just gave you the formula for the angular fringe width or angular separation right over here. It is nothing but beta by d, right? I just gave it to you right over here. So let's put it over here. It is nothing but beta by d. Beta is lambda capital D by small d, this by d. So dd cancels, so it will become lambda by d. So the angular separation fringe width is lambda by d. Now let's see what is given in the questions. What is given in the questions? If the screen is moved away, the separation remains the same. Yes, correct. This is correct because it is independent. It is independent. The D got cancelled. Independent of capital D. So definitely statement 1 is correct. A monochromatic source of larger wavelength. Oh, this I think might be problem. If lambda is more, then this should not decrease. This should definitely increase, directly proportional. This says decreases, so this is wrong. So first is correct, second is false. So I think it should be B option. Yes, it is B option. It is B option. Very good, Meghna. Awesomeness. Proud of all of you. Great, great. Very good, guys. Very good. Now, the next is basically your diffraction and polarization. Let me quickly go through that. When you have a narrow slit, when you have a narrow slit whose width is A, it's a single slit experiment. It's a single slit experiment. And you have a screen. You will see that if light is coming from here, these are the wavefronts of the light. If light is traveling like this, okay, so this is monochromatic light, which is incident, whose wavelength is lambda. you will see the light will spread. Yes, it will spread in all the directions, and it will cause interference, and it will create a pattern on the screen just like before. You will see, just like before, you will see an interference pattern being formed, but it is slightly different. I mean, the fringe width formula is different, and also the intensity variations are slightly different, meaning exactly in the front, you will still get a bright fringe. You will still get a bright fringe, no doubt. But the next bright fringe will not be so bright. The next bright fringe will not be so bright. The next bright fringe will not at all be so bright. After that, after that, it will be hardly any bright. You will hardly be able to see it. So the intensity keeps on reducing, which is not the case, for your Young's double slit experiment. This was your Young's double slit experiment. Two slit experiment, intensities were same, but here you will see the intensities gradually reduce. Okay, that is number one. Now let's assume this particular distance from here to here again to be capital D, again much larger than A. Then for any minima that you want, the angular location, the location of any nth minima. Okay, this is basically your theta. So the angular position of minima, meaning the dark fringes, theta is given by n times lambda by A. Sorry, n times lambda capital D by A. Sorry guys, my bad. Sine theta will be nothing but n times lambda by A. This is fine. Sine theta will be n times lambda by A. This is the formula for any minima. This is, let's say, your nth. This is your nth dark fringe. Nth dark fringe is given by n times lambda by A. So, if you want to find what is the actual distance that y coordinate is given by, think about it, it's a right angled triangle. So, y will be nothing but almost d into tan theta, but tan theta will be almost sine theta. So, it will be d sine theta, which will give me capital D, or rather that same thing, n times lambda capital D divided by A. So this is the y coordinate, which will be n lambda D by A for any nth minima. That is the y coordinate of any nth dark fringe or minima. Very, very important here. The formulas are usually used for minimas only. They are generally not used for maximas. Generally, you do not study the questions for maximas, but if at all needed, I'll just give you the angular position of maxima will be sine theta is equal to odd times lambda by 2a. That is what the main difference will be. The difference over here will be, instead of tan you will put sine, but the value of sine will be odd lambda by 2a. That's it. That's the major difference which you should know. Usually they will not give you, because in NCERT also it is not there. Only for minimas you solve the questions, but still I'm blocking it for you. The last thing is, what is the width of the central maxima? It starts from first minima on either side. This is W, which is called as the width of the central maxima. The width of the central maxima. This particular width will be 2 times lambda capital D divided by A. Yes, 2 times lambda capital D divided by A. This is something which you should be aware of. Okay. So these are the major formulas which are there in this particular diffraction, which you should know. I have highlighted all of this, and diffraction means spreading of light. Diffraction, what is the meaning of it? It is the spreading of light. It is the spreading of light when it passes an obstacle or a slit or basically an aperture. Anytime it passes any of these, it will spread. That spreading is called as diffraction. Okay, let's do some questions based on this. NEET 2015, for a parallel beam of light, wavelength lambda, everything is as standard. Slit width is A. Distance is the screen distance from the slits. Width of the central maxima. Guys, direct question. Direct question came. Yes. Yes, I'll be coming, Dharneshwaran, on the G channel. Just 1 second. Yeah, direct question, guys, came in NEET 2015. 2 lambda d by A. That's it. So 2 lambda d by A, which is option A. Direct question has come. Can you believe it? Such a simple thing. Okay. Moving on to the next question. NEET 2019. Angular width of the maxima is this much for wavelength of this much. When new light is used, the width reduces by 30%. What is the wavelength? We just saw that the angular width, the width of the central maxima, is given by 2 lambda d by A. So the width is directly proportional to lambda. Now, as per the given information, the the angular width is decreased by 30%. So what will be the new width? It will be the old width minus 30% because reduction. So this will be W minus 0.3 W. So it will be basically 0.7 W. So what can you say about the wavelength? It is directly proportional. So therefore, the new wavelength will also be 0.7 times the old wavelength. So 0.7 times old wavelength. Old wavelength was 6000 Armstrong. 7 6 are 42. So this will be 4200 Armstrong, which is C option. Very cool. Awesomeness. Great. Shall we go ahead to the next question? Guys? Okay. So I think the next is directly polarization. So let's go to polarization now. Okay. Now, some basic laws are there in polarization. I will tell you that. And what is the meaning of polarization also, I'll tell you. See, our light which is there, it's an electromagnetic wave. We all know that. This is, let's say, your electric field, and the magnetic field is obviously perpendicular in direction. Okay, so this is your magnetic field. So if electric field oscillates like this, the magnetic field oscillates like this, and the direction in which the light actually goes is perpendicular to both of them. This is the direction of the ray of light. Now, this particular plane, which contains the electric field, is considered as the plane of oscillation of that electromagnetic wave, or basically light. And such a wave which has only one plane of oscillation is called as a polarized wave. So if you have light whose oscillations are only in one direction, okay, then it is said to be polarized light or polarized wave. But if the oscillations are here, everywhere, I mean all the directions, it is random, it is then said to be unpolarized light. Now, your bulbs, etc., tube lights, your normal light is usually unpolarized. The normal light that you get from tube light bulbs, etc., is unpolarized. Even the sun, whatever light you get, is unpolarized. But specific laser beams are there which emit polarized light, So in polarized light, electric field has only one direction of oscillation. In unpolarized light, the light will oscillate in different planes. Now, there are these devices called as polarizers, which can change the plane or which can allow only those fields which are in a unique direction. So, when we use something called as a polarizer, when we use something called as a so let's say this is a polarizer. This is your polarizer. Polarizer has this unique property called as a pass plane. It has something called as a pass plane. So let's say, for example, this is the pass plane. Make it smaller. So this is example, or pass plane or pass axis, sometimes it is called. So let me show the pass axis, that is better. This is called as the pass axis, and that plane will be called as the pass plane, which allows only those fields which are oscillating in that particular axis or direction. So say for example, you get a light which is polarized, but the oscillations are in a different plane. The oscillations are in a different plane. So by the time the light enters the crystal or the polarizer, it is already making some angle theta. Let's say the incident polarized wave, incident polarized wave had an intensity of I. Because the passing plane makes an angle theta, it will only allow those electric fields which are in that direction. So the outcome is a smaller intensity because only a component will be allowed. So the outcome is again polarized wave. It's again a polarized wave, but with a different new intensity. That new intensity which comes out is that old intensity into cos square theta. This particular law is called as Maloo's law. What is it called? It is called as Maloo's law. Keep that in mind. What is it called? It is called as Maloo's law. Everybody with me? Very good. So the new intensity will be less and the plane is now polarized in that pass axis. So the intensity is slightly less. But what happens if you pass completely unpolarized light? That means the oscillations are in all the possible directions. And let's say this is unpolarized light. Let's say again, this is our pass axis. You will see the final light will still be polarized. It will still be polarized. So all the other components will get off. So if the original intensity was I, the polarized light will have an intensity of I by 2. The intensity will become half. Half of the components will go, only one half of the components will be remaining. So that's why intensity will become half. Keep this in mind. So this is the new intensity. This is the new intensity of light. Is this absolutely clear, everyone? Okay. Last thing over here, if you have a medium, if you have some medium, let's say this is your medium whose refractive index is mu, and let's say this is our normal, and you have unpolarized light, you have unpolarized light falling onto it. Some of the light will obviously get reflected some of the light will obviously get refracted. So this is the light which is getting refracted, and this is the light which is getting reflected. If by chance it so happens that the refracted light is perpendicular, yes, it is perpendicular to the reflected light, and this is unpolarized. This is unpolarized incident light. Unpolarized incident light. That means it will have oscillations in all the possible directions. Yes, in all the possible directions. The reflected light will become completely polarized. It will become completely polarized. This refracted light will become partially polarized. This will become partially polarized. Yes, this will become partially polarized. And this will happen when the reflected and the refracted light rays are 90 degrees. That means they are perpendicular to each other. And this angle which is there, this is called a special angle called as the Brewster's angle. Brewster's angle. And the law is also called Brewster's law, such that tan of that Brewster's angle is going to be the refractive index of that medium. Tan of that Brewster's angle is going to be the refractive index of that medium. So this is another important law, Brewster's law, which talks about how the reflected light gets polarized. All these are again very important things. Let's go to some questions. NEET 2022. A linearly polarized light of 10 intensity is incident on a polarizer. The angle between the polarization of the light and that of the polarizer such that intensity of the output light is 2.5 lumen. So what is that angle? That is the question. Guys, come on. How are you going to solve this? Think about it. Is this based on Malu's law? Yes or no? Just think about it. So there is already light which is polarized having an intensity of 10. It passes some polarizer. And finally the light which comes out is of different intensity. Why is it of different intensity? Because it is at an angle. How much intensity it is? 2.5. Now we all know by Malu's law, final intensity is initial intensity cos square theta. So this will be 1/4 is cos square theta. So cos theta will be half. So theta will be 60 degree. So they asked angle between the direction of the polarization of the light and that of the polarizer. Well, that is directly 60 degree. That is the answer. Yes, very good. Perfecto. Awesomeness. Next one. Polarites P1, P2 are placed with the axis perpendicular. Unpolarized light is incident on P1. A third polarizer is kept in between P1 P2 such that the axis makes 45 degrees with P1. The intensity of the transmitted light is how much? Okay. So I'll tell you how it is. Your first polarizer is like this. Second polarizer is here. And another polarizer is making an angle of 45 degrees. Okay. Now the pass axes are as follows. This is the pass axis. This is the pass axis. It's perpendicular like that. Okay. Here you get unpolarized light. Here you get unpolarized light. So this was P1. This was P2. The third polarizer is here. Okay. P3 is kept between P1 and P2. When you pass unpolarized light, whose intensity is I naught, after coming out of it, its intensity will become obviously I naught by 2. Once it goes from here, the light will again be polarized but in a new direction. This intensity will be I naught by 2. I naught by 2. Angle is 45 degrees. So cos square 45, which is I naught by 2. Cos 45. What is cos 45? 1 by root 2. 1 by root 2 whole square. So 1 by 2 into 1 by 2 is 1 by 4. So I naught by 4. So I naught by 4 will be the new intensity from here. But what will happen again? It will further get polarized like this. This intensity will be whatever this intensity was there, I naught by 4 into cos square 45 again. So this will become I naught by 4. Cos 45 is again 1 by root 2, but square it. So 1 by 2 into 1 by 4 is 1 by 8. So I naught by 8. I naught by 8 should be the answer. Is that right, everyone? I naught by 8. Yes, option C. Clear, my dear students? Perfecto. Everyone? Yep, C for Captain Shreyas. Perfect. Yes, so we are done with this particular session. Okay, awesome, guys. Awesome. Some students were also asking, sir, for optical instruments, can you just give us the formulas? So I'll just give you the formulas and keep just in case for optical instruments. See, regarding optical instruments, just remember these formulas. Optical instruments. First formula is for, in general, something called as magnifying power. Magnifying power. It's just a ratio. It is not the same as magnification. That is completely different. This magnifying power is how much angle is subtended with the instrument upon how much angle is subtended to the naked eye. Meaning, if you are seeing something, it subtends 5 degrees, but with the instrument, it becomes larger, maybe 10 degrees. So from 2 degrees, it becomes 10 degrees. It has become 5 times more. So that is magnifying power. On telescopes, microscope, you will see 10x, 5x, 100x, 200x. That is basically, if that angle is there by that object, how many times will it be magnified? That is called as magnifying power, which is usually the case for all the optical instruments. Okay, that is what is given to you. Now, if it is a simple microscope, for a simple microscope or basically magnifying glass, what is the formula? The formula is, there are two formulas. First formula, magnifying power for normal vision is just least distance of distinct vision by f. Magnifying power for maximum best vision, which is for least distance of distinct vision, is 1 plus d by f. These are the two formulas, normal vision and other is least distance of distinct vision. If you are asking what is d, etc., d is that least distance for which you can see things clearly, this distance of distinct vision. For a normal average adult, it is approximately 25 centimeters. Next formula is for a compound microscope. Normal microscope which you use in your biology lab. For that, the formula is as follows. Magnifying power is equal to, you have basically length of the tube of the microscope by the focal length of the objective into 1 plus least distance of distinct vision upon focal length of the eyepiece. This is the formula. This is the formula which you will use for compound microscope. Here L is the length of the tube. This is always the image distance plus the object distance. So it is the length of the tube. Length of the tube of that microscope. Length of the tube of that microscope. Lastly, you have the telescope. Guys. So for telescope, what's the formula? The magnifying power is nothing but Fe by Fo, objective and eyepiece. That's it, focal length ratio. And the length of the tube of the telescope is the addition of the focal lengths of the eyepiece and the objective. That's it. This one and this one. Just one small correction. This was FO by FE. Yeah, this was FO by FE. Yeah, correct. Perfect. Okay, so that is what it is. So thank you guys so much for joining in. Do not forget to like this video and also subscribe.